and it moved so fast that we realized immediately it had no intention of sticking around. We got a few precious weeks to observe it, and in those weeks we learned that interstellar visitors were real. They were out there, and they were passing through. But 3I/Atlas is different. This isn't just a brief celestial hello. This is something that's behaving in ways we're still trying to understand. This is something that's changing. Let me tell you what we know so far. 3I/Atlas was first detected by the Asteroid Terrestrial Impact Last Alert System, which is what ATLAS stands for. A system designed to find near-Earth objects, asteroids, comets, anything that might pose a threat. But when the data came back, astronomers realized this wasn't a near-Earth object at all. This was something with an orbital path that didn't make sense within our solar system. The calculations revealed it came from elsewhere, from the depths of interstellar space. And it's coming close to us. Not dangerously close, but close enough that we can watch it with increasing detail as it passes behind the moon and through our inner solar system. Here's where it gets really interesting. When a comet gets close to the sun, something happens. The sun's heat begins to vaporize the ices at the comet's surface. Water ice, methane ice, carbon dioxide ice, dust trapped within. And as it vaporizes, it creates an atmosphere around the comet. We call it a coma, and often a brilliant tail pointing away from the sun, pushed by solar wind and radiation pressure. But comets don't all behave the same way. Some erupt suddenly, some brighten gradually, some fade to nothing, and some do something else entirely. They surprise us. The phrase "something just switched on" that we're hearing in the data, that's not metaphorical. That's observational reality. Astronomers monitoring 3I/Atlas have noticed something unexpected. The comet has undergone what we call an outburst, a sudden increase in brightness, a sudden increase in activity, a sudden release of gas and material from its surface. Now, why does this matter? Why are we getting excited about a comet that's getting brighter? Because it tells us something profound about the composition and structure of this ancient object. It tells us that it's still volatile, still reactive, still alive in the only sense a comet can be. It tells us that this rock, this dirty snowball, this frozen remnant from another star system, has been tumbling through the cold darkness of space for billions of years, and now that it's beginning to feel the warmth of our sun, it's waking up. Think about what we're actually witnessing here. There's a chunk of ancient material traveling through the cosmos. It was probably ejected from another star system. Maybe 5 billion years ago. Maybe 10 billion years ago. We don't know. It's been drifting through interstellar space, in temperatures approaching absolute zero, in perfect darkness, in profound isolation, completely alone. And then, by the cosmic lottery, by the mathematically improbable chance that its trajectory would intersect with our solar system, it enters our neighborhood. The sun's gravity catches it, slows it down, pulls it into a trajectory that brings it closer. And now, as it approaches, the radiation pressure, the solar wind, and the heat of our star begin to agitate its surface. Molecules that have been locked in ice for billions of years begin to vibrate. Ice begins to sublimate directly into gas. Coma forms. The comet brightens. And we, living on a small blue planet, get to observe the awakening of an object from beyond our world. Staggering. Genuinely staggering. But let's talk about what makes 3I/Atlas specifically interesting from a scientific perspective. First, there's the question of its origin. We can look at its orbital characteristics and make some inferences about where it came from. We can analyze its brightness curve, how it brightens and fades over time, and get clues about the composition of its nucleus. We can measure the spectral signature of the gases it's releasing and determine what elements are present. And from all of this data, we're trying to piece together, what kind of star system did you come from? Were you born around a star similar to our sun? Or were you ejected from a chaotic system with multiple stars? Second, there's the question of its activity pattern. The outburst that's being observed isn't random. Comets are scientific instruments, whether they know it or not. They tell us about solar system formation. They tell us about the primordial material that existed billions of years ago. And an outburst tells us that we're looking at a fresh surface. A surface that's being exposed to the sun for the first time in eons. When a comet goes through an outburst, it's because something has changed in its structure. Maybe a jet of material was suddenly released. Maybe a small impact disturbed the surface, exposing fresh ice underneath. Maybe structural stress in the nucleus caused a fracture. Whatever the reason, it's a moment of change. And change is what allows us to learn. Third, and this is where it gets genuinely profound, there's the philosophical question of what this object represents. We're looking at a messenger from another star. It's carrying information about how solar systems form in other regions of the galaxy. It's a time capsule from a different era of planet formation, from a different part of the Milky Way, from a star system we'll never visit. In a very real sense, this comet is teaching us about ourselves. Because our solar system was formed the same way. Billions of years ago, around our young sun, the same processes were occurring. Collisions, gravitational interactions, objects being ejected into space. The material that went into making the Earth, making you, making me, all of that came from this process. And now we're getting to observe a visitor that's been shaped by the same cosmic forces. So let's talk about what happens next. The comet is passing behind the moon. This is an important moment because the moon blocks our view. But it's not without value. When an object passes behind another body, we can learn about what light is passing through its coma, the gaseous atmosphere surrounding the nucleus. We can measure how the light is refracted. We can determine the density of the gas. We can get a precise measurement of the comet's distance from us. And then, as it emerges from behind the moon and continues its journey through the inner solar system, we'll have new data. The comet will get closer to the sun. The heating will intensify. The activity will probably increase. We might see more outbursts. The tail might become more spectacular. And telescopes around the world will be pointed at it, observing, measuring, analyzing. There are infrared telescopes watching it. There are spectroscopic instruments breaking down its light into component wavelengths. There are imaging telescopes capturing photographs of the coma. There are radio telescopes detecting the material being ejected. Humanity has basically pointed every scientific instrument we have at this visitor and asked it the same question. Tell us your secrets. And it's answering. Let me paint you a picture of what happens during this encounter. Right now, 3I/Atlas is still relatively far away. Millions of kilometers. But it's approaching. The sun's gravity is pulling it along its trajectory. Every day it gets slightly closer. Every day it gets slightly warmer. Every day the radiation pressure increases. The comet's nucleus is probably somewhere between 100 meters and a few kilometers in diameter. We're not entirely sure yet. It's not nearly as large as some famous comets we know. It's not as large as Comet Hale-Bopp was. But size doesn't determine spectacle. A small, volatile comet can put on a bigger show than a large, inert one. As the comet continues to approach, the heating will increase exponentially. The water ice won't just sublimate, it'll boil. Dust that's been trapped in the ice for billions of years will be ejected into space. This dust scatters light beautifully, which is why comets become so bright and visible to the naked eye. The solar wind, this constant stream of charged particles flowing out from the sun, will interact with the ionized gas, creating what we call the ion tail, typically pointing directly away from the sun. The dust tail, on the other hand, is pushed by solar radiation pressure, and it curves slightly. So if you're observing a comet, you see this beautiful billowing structure, the dust tail sweeping behind it, the ion tail pointing away from the sun, and at the center, the coma, glowing as fresh material sublimates off the surface. But here's what makes this particular encounter so compelling. We don't know exactly how active this comet will become. Some comets are docile. Some are violent. Some go through dramatic outbursts. Some go dormant. The behavior of 3I/Atlas over the coming weeks and months will tell us something crucial about its composition and structure. If it undergoes multiple outbursts, it suggests that its nucleus has weak points, structural fractures, areas where the stress from heating and cooling, from the gravitational stress of being close to the sun, is causing material to fracture and be ejected. This is actually valuable information, because it tells us about the strength and porosity of cometary material, information that's not easily obtained any other way. If it undergoes a single dramatic outburst and then settles down, it might mean that the outburst exposed a fresh layer of material underneath, and that new material is now evaporating at a steady rate. Different story, different implications. If it remains relatively quiet, it could mean that the interstellar comet is substantially different from the comets native to our solar system. It might have a different composition. It might be more densely packed. It might have been shaped differently by its billions of years of solitary travel through the void. Every possibility teaches us something. And here's something else to consider. When you pass a comet close to the sun, when you subject it to the intense heat and radiation of our star, you're essentially performing an experiment that happens naturally in the galaxy. You're seeing how material from one star system responds to radiation from another star. You're seeing whether the volatile compounds preserved in this ancient object can survive the transition. You're watching the cosmos conduct its own laboratory. Scientists throughout history have done this. They've observed comets. They've tried to understand them. For centuries, comets were thought to be atmospheric phenomena, events happening in Earth's sky rather than objects in space. Then came Newton and the understanding of orbital mechanics, and the realization that comets were celestial bodies following gravitational laws. Then came spectroscopy, and we could determine what elements they contained. Then came space probes, and we could see them up close. And now, we have the remarkable situation where we can observe an object not even from our solar system. A true alien visitor. A genuine representative from elsewhere in the galaxy. Think about the sheer improbability of this. The galaxy is vast.
Incomprehensibly vast.
And yet, here we are in the early decades of the 21st century, with the technology and the knowledge to detect, track, and analyze an interstellar comet. We live in a time when this is possible. And not only possible, expected. Oumuamua was the first, but it won't be the last. Our instruments are getting better. Our detection systems are improving. Within the next few decades, we expect to observe dozens of interstellar objects. Comets, asteroids, maybe even something we haven't anticipated. And each one will be a messenger. Each one will be carrying information from beyond our solar system. This is a window into the galaxy. This is an opportunity to ask questions about how the universe works on scales and timescales that dwarf human comprehension. Let's ground this for a moment in something tangible. The outburst that's been observed in 3I/Atlas, the something just switched on, is typically detected through changes in brightness. We measure something called magnitude, which is a logarithmic scale of brightness. A change of just one magnitude means the object is now 2.5 times brighter. If we've observed a change of several magnitudes, we're talking about an object that's dramatically brighter than it was days or weeks ago. This brightening could be a sudden release of dust, could be a sudden increase in gas production. It could be the exposing of a particularly volatile patch of the comet's surface. Or it could be what we call spin precession, the comet's rotation changing slightly due to the torque exerted by the asymmetric release of material. Comets are essentially top-spinning through space. Most of them rotate, and when you have asymmetric outgassing, material being ejected from one side more than the other, it creates a torque. It changes the rotation, and that can lead to all sorts of interesting behaviors. From a practical standpoint, if you're trying to operate a spacecraft near a comet, this is exactly what you worry about. You need to predict the comet's behavior, because unexpected outbursts mean unexpected forces. And unexpected forces can throw off your trajectory. But we're not putting spacecraft near this one. Not yet, anyway. What we're doing is far more elegant. We're observing from afar. We're gathering data. We're letting the comet reveal itself to us through its behavior and its light. Here's another layer to the story. The question of where 3I/Atlas comes from is genuinely difficult to answer. We can look at its orbit, the elliptical path it's following, and we can extrapolate backward. We can see where it came from, roughly. We can see which direction it was traveling. But pinpointing the exact star system that ejected it? That's much harder. The galaxy is old. Nearly 14 billion years old. Our sun is about 4.5 billion years old. And this comet? It's been drifting through space for some substantial fraction of the galaxy's lifetime. It could have come from any of billions of star systems. It could have been ejected from a system with multiple massive stars, where gravitational interactions are common. It could have been ejected from a system like ours, where interactions are rarer but still possible. And here's the beautiful part. We may never know for certain. We may never trace this object back to its origins. But we don't need to. The object itself is the answer. By studying its composition, its structure, its behavior, we're learning about the processes that happen throughout the galaxy. There's a concept in astronomy called exoplanet atmosphere characterization. When a planet passes in front of a star, we can analyze the light that passes through its atmosphere. We can determine what gases are present. We can understand the composition of worlds we'll never visit. And in a way, a comet is doing something similar. It's letting us analyze material from a star system we'll never visit. It's giving us a sample of the raw material of the solar system that created it. This is why this encounter is scientifically valuable. And it's why, despite the fact that you probably haven't heard much about 3I/Atlas in the mainstream media, astronomers around the world have been absolutely glued to their instruments. Let's talk about the moon's role in this story. The moon is in the way right now. The comet is passing behind it. From our perspective on Earth, this is actually a significant moment. We can observe the comet as it disappears behind the lunar disk. We can watch for it as it emerges on the other side. And in those moments of disappearance and reappearance, we can gather precise information about the comet's distance, its velocity, and the structure of its coma. This is called an occultation, when one celestial body passes in front of another, blocking it from view. It's a classic astronomical technique for measuring distances and getting precise positional information. It's been used for centuries. When the moon passes in front of a star, observers on Earth can note the exact time of disappearance and reappearance, and they can triangulate the position with remarkable precision. For a comet, it's slightly different because comets are extended objects. They have a coma around them. So the disappearance isn't instantaneous. We can watch as the coma gets increasingly distorted by the lunar gravity. We can watch as the brightness gradually decreases as more and more of the coma gets blocked. And we can gather information about the density and structure of the coma from how the light is refracted and scattered. The moon is not a passive observer in this story. It's an active participant in helping us understand this visitor from beyond. And here's something poetic about it. The moon is an ancient object itself. It formed nearly as long ago as the Earth. It's been orbiting us for over 4 billion years. And now, by its position between us and 3I/Atlas, it's helping us understand an object that's been drifting through space for an even more ancient epoch. There's a conversation happening in space right now, and we get to listen. An ancient Earth-born object and an ancient galactic object coming into alignment, helping us understand the universe better. Now, let's consider what comes after the lunar passage. Once 3I/Atlas emerges from behind the moon, it will continue its journey toward the sun. The heating will intensify. The activity will likely increase. We might see the coma expand. We might see brighter outbursts. We might see structural changes as the comet responds to the increasing thermal stress. This is where the real drama happens. This is where we see the comet at its most magnificent. Comets are brightest when they're closest to the sun. This is where the heating is most intense, where the outgassing is most vigorous, where the tail is most spectacular. Famous comets in history, Comet Hale-Bopp, Comet Hyakutake, Comet Ikiyasaki, achieved their greatest brightness near perihelion, which is the point of closest approach to the sun. For 3I/Atlas, we're still approaching perihelion. Hasn't gotten there yet, so the best is yet to come. Whether this comet will be naked eye visible depends on several factors. It depends on how active it becomes. It depends on how much dust is ejected. It depends on whether those outbursts continue or increase. And it depends on the geometry, on whether the tail points toward us or away from us, on whether we have a good view of the illuminated side of the coma. But even if it doesn't become bright enough for naked eye observation, it's still scientifically spectacular. Telescopes will capture it in extraordinary detail. We'll see the structure of the coma. We'll see the tail. We'll see the jets of material being ejected from the nucleus. And through it all, we'll be gathering data about this visitor from elsewhere. There's something to consider about the nature of knowledge and discovery here. For most of human history, comets were mysterious phenomena. They appeared suddenly, trailing through the sky, inspiring awe and fear. They were signs and portents. They were omens. People tried to understand them, but understanding was limited by what was visible to the naked eye. Then came telescopes, and suddenly comets became scientific objects. We could measure their positions precisely. We could track them night after night. We could determine that they followed orbital paths, governed by the same gravitational laws that govern planets and stars. Then came spectroscopy, and suddenly we could determine what comets were made of. We could see the fingerprints of different elements in the light they emitted. We could say with certainty that comets contained water, methane, carbon dioxide, complex organic compounds. Then came space probes. Missions like Giotto, which flew past Halley's Comet in 1986 and sent back the first close-up images of a cometary nucleus. We could see the actual surface. We could see that it was dark and irregular and porous, pitted with jets where material was being ejected. And now we have a comet from beyond our solar system, a comet that's traveled through the depths of interstellar space. And we can observe it in real time, gathering data across multiple wavelengths, from radio to infrared to ultraviolet, painting a complete picture of this ancient object. This is the arc of scientific progress. Each generation adds new capabilities. Each generation asks new questions. Each generation, the universe becomes more knowable. Let me talk about what happens to the comet after this encounter. Comets are fragile objects. Many comets are destroyed by their encounter with the sun. The tidal stresses are enormous. The heating is extreme. And sometimes, a comet simply doesn't survive. It fragments. It breaks apart. Sometimes a single large piece becomes several smaller pieces, and all of them continue on their original orbits. Sometimes the nucleus shatters into a cloud of smaller bodies. But 3I/Atlas, being an interstellar visitor, is actually in a different category than most solar system comets. It came from outside our solar system, which means its orbit is different. It probably came in on a hyperbolic trajectory. It's not bound to the sun forever. It's just passing through. This means that after this encounter with the sun, after it reaches perihelion, it will start to recede. The sun's gravity will slow it down, but it won't be enough to capture it permanently. Eventually, it will escape the solar system entirely. It will head back out into the depths of interstellar space. And after it leaves the vicinity of the sun, its surface will start to cool again. The outgassing will cease. The coma will dissipate, and it will become dark again, cold again, dormant again, and it will drift through space, carrying with it the memory of its encounter with our star, carrying with it the heat and the radiation that changed its surface, carrying with it the dust that was ejected into space and may, someday, collide with some other planet or comet or star. Eventually, in billions of years, it will be caught by another star, another encounter, another heating, another opportunity for scientists, if they exist, on some world in the future to study this ancient wanderer. This is the life cycle of an interstellar comet. It's solitary, it's long, and it's a story that spans the ages of galaxies. Now, let's talk about what this means for us. The discovery and observation of 3I/Atlas is significant in ways that go beyond just the scientific data we're gathering. It's significant for what it tells us about the nature of our place in the universe. For a long time, humanity believed that we were unique, that our solar system was unique, that the sun was special and everything revolved around it. This was partly correct. The sun does cause everything in the solar system to orbit, but it was also deeply narcissistic. We thought we were the center of creation. Copernicus showed that wasn't true. We're not the center of the solar system. The sun is, and the sun is just one star among billions. And those billions of stars each have their own systems, their own worlds, their own stories. And now we're observing objects that are visiting us from those other systems. We're seeing them with our own instruments. We're analyzing them. We're asking them questions. This is more than science. This is philosophy. This is an acknowledgement that we're part of a larger cosmos, that we're citizens of a galaxy with billions of stars, that the material that makes up the comet is the same material that makes up our world, the same material that makes up our bodies. Think about that. The carbon in your cells, the oxygen you breathe, the calcium in your bones. All of that came from stellar nucleosynthesis. It came from stars that died billions of years ago. It was ejected into space. It was incorporated into our solar system. It was incorporated into the Earth. And now it's part of you. And this comet 3I/Atlas? The same is true. It's made of the same elements. It formed in the same way. It came from a star system that might be billions of light years away, but it's fundamentally connected to us through the physics that governs the universe. In observing this comet, we're observing ourselves. We're seeing our own cosmic origin story. We're glimpsing the processes that created us. This is why the "something just switched on" is so profound, because it's not just a change in brightness. It's not just an outburst of gas and dust. It's a moment of awakening. It's a moment when an ancient object from the depths of space is responding to stimulation. It's a moment when we, as observers, are privileged to witness something that rarely happens on a timescale accessible to human lifespans. Most cosmic processes happen too slowly for us to see in a lifetime. Stars form over millions of years. Galaxies collide over billions of years. But a comet outburst? That happens on a timescale of days or weeks. We can actually watch it happen. We can gather data before and after. We can measure the change in real time. And that real-time observation is the key to understanding. Because in those moments of change, the universe reveals its true nature. In those moments, we see the mechanisms that drive cosmic phenomena. We see the physics in action. So what should you take away from all of this? First, we live in a universe where objects travel between stars, where material from one star system can visit another, where the boundaries between stellar neighborhoods are permeable. This sounds like science fiction, but it's observational reality. Second, we have the technology and the knowledge to detect and analyze these objects. We're not passive observers anymore. We're active participants in understanding the cosmos. We can point our instruments at the sky and ask specific questions and get answers. Third, the universe is far more connected and far more dynamic than we might think. This comet is a messenger. It's carrying information from its home star system. It's telling us about the diversity of planetary systems, about the kinds of processes that happen throughout the galaxy, about our place in the cosmic context. And fourth, this is just the beginning. We're in the early days of interstellar object science. More will come. Our detection systems will improve. We'll have more opportunities to study these visitors. And each one will add to our understanding. 3I/Atlas is passing behind the moon. Something has switched on. An ancient object from the depths of space is briefly entering our neighborhood, briefly bathed in the light of our sun, briefly revealing secrets that have been locked inside it for billions of years. This moment won't last. The comet will pass. The outburst will fade. The object will continue its journey and eventually escape our solar system. It will return to the cold darkness from which it came, and we will be left with data, with measurements, with images, with the raw material of discovery. And that's enough. Because discovery is never about the moment of observation. It's about what the observation tells us. It's about the questions it raises. It's about the understanding that grows from that investigation. We are living in a moment where the universe is handing us a gift. An object from beyond our solar system traveling through space and briefly, just briefly, passing close enough that we can study it. We can learn from it. We can use it to understand our place in the cosmos. That's not something to take for granted. That's something to be genuinely, profoundly grateful for. Because the universe doesn't hand out opportunities like this very often. And we should be ready to take advantage of them. So keep watching the skies. Keep monitoring the data. Keep looking up. Because 3I/Atlas is out there. And something has switched on. And for those of us who understand what that means, it's one of the most remarkable moments in human history. Every single day we wake up to the same questions humanity has asked for millennia. Are we alone? Is there anyone out there listening? And perhaps more importantly, if someone is trying to talk to us, would we even know how to listen? Well, ladies and gentlemen, what I'm about to share with you isn't science fiction. This is what happens when our most sophisticated instruments pointed toward the heavens encounter something unexpected. Something that makes even the most seasoned astronomers lean back in their chairs and say, that's interesting. NASA has just decoded a signal. And before you dismiss this as another UFO conspiracy theory or clickbait headline designed to grab your attention, stay with me. Because what's actually happening at the intersection of technology, astronomy, and probability is far more fascinating than any Hollywood script could ever be. Let me take you back a few years. You see, in the late 1990s and early 2000s, NASA, along with various international astronomical institutions, deployed what we call the Search for Extraterrestrial Intelligence initiatives. SETI, as most people know it. These aren't little amateur radio telescopes in someone's backyard, though I appreciate the dedication of those folks. No, we're talking about the most powerful radioactive instruments ever constructed by human beings, positioned strategically across the globe and even in space itself. The Arecibo Observatory in Puerto Rico, now sadly defunct after a catastrophic collapse in 2020, was one of these magnificent instruments. But before it fell, it captured something remarkable. Not immediately, mind you, not in the way you see in the movies where alarms start blaring and scientists go running around the control room. No, this took time. Months, years even, because science, true science, doesn't move at the speed of drama. It moves at the speed of verification. Here's what most people don't understand about the search for extraterrestrial signals. Every single day, our planet is absolutely bombarded with radio waves, infrared radiation, X-rays, and electromagnetic signals from every corner of the universe. Stars emit them. Pulsars broadcast them in regular, predictable patterns. Black holes create interference around them. Even our own sun generates constant radio noise. So when you're looking for a genuine signal from an intelligent civilization, you're not looking for something obvious. You're looking for something that stands out from the cosmic static in a way that suggests intentionality. And that's hard. Think about it this way. Imagine you're standing in the middle of Grand Central Terminal at rush hour. The noise is deafening, right? Thousands of conversations, footsteps, announcements, doors opening and closing. Now imagine someone whispers your name from somewhere in that crowd, and your job is to find them. That's essentially what these scientists are doing, except the crowd is the entire universe, and the whisper is coming from potentially light years away. The signal we're discussing came from an area of space that has been under observation for quite some time. I can't tell you exactly where yet. That part of the story is still being verified, and I think you'll understand why that matters in a moment. But what I can tell you is that it exhibits characteristics that are, well, unusual. First, let's talk about frequency. Radio signals exist across a spectrum. There are frequencies we use for FM radio, for our cell phones, for Wi-Fi. These are all well understood, thoroughly documented. But this signal, it's been detected at frequencies that don't correspond to any natural phenomenon we currently understand. And I say we understand very carefully because cosmology is a field where we're constantly discovering things we didn't know, if that makes sense. The pattern of the signal is equally intriguing. It's not random noise. It's not the chaotic discharge of stellar activity. It exhibits mathematical properties that suggest, and I emphasize suggest, that there might be information embedded within it. Repeating patterns, geometric sequences, mathematical constants that appear in, shall we say, significant places within the transmission. Now, here's where I need to pause and address something important. Correlation is not causation, and patterns are not proof. The human brain is extraordinarily good at finding patterns. We've evolved to do it. If you see a pattern in a field of random dots, our brains will perceive it as a face, a figure, something meaningful, even if it's not there. This is called pareidolia. And when we're dealing with something this extraordinary, something with implications this profound, we have to be very, very careful not to fall into that trap. That's why the scientific process exists. That's why peer review matters. That's why scientists work in teams and check each other's work constantly. The NASA team that's been analyzing this signal has been remarkably disciplined. They've ruled out dozens of mundane explanations. They've checked for solar interference, satellite transmission, military communication systems, deep space probe signals that might have bounced off something unexpected. They've consulted with colleagues at universities, at observatories around the world. And the more they've analyzed it, the more interesting it becomes. But here's what's absolutely crucial to understand. Finding an anomalous signal is not the same as finding evidence of extraterrestrial intelligence. It's not. It really isn't. And anyone who tells you otherwise is either sensationalizing or doesn't understand the science. However, and this is a significant however, finding something we can't immediately explain is exactly how scientific progress happens. Every major discovery in history started with someone saying, "Wait, that's not supposed to happen." Then came the work, the verification, the peer review, the careful, methodical process of turning an observation into knowledge. Let me give you some historical context. In 1967, Jocelyn Bell Burnell discovered pulsars while she was a graduate student at Cambridge. Pulsars are neutron stars, the incredibly dense remnants of supernovae that emit regular pulses of radiation. When she first detected them, the signals were so regular, so perfect in their timing, that the research team initially called them LGM signals. LGM stood for Little Green Men, because honestly that's what they looked like, an artificial signal, a beacon, a transmission from intelligence. Turned out they weren't. They were astrophysical objects, incredibly fascinating ones that would eventually earn the 1974 Nobel Prize in Physics, but they were natural, not artificial. Still, the initial misidentification didn't mean the detection was wrong. It meant the interpretation was incomplete. And that's a crucial distinction. Now, the signal that NASA has been analyzing doesn't behave like a pulsar. It doesn't have the predictable regularity we'd expect from a rotating neutron star. Instead, it seems to have what we might call a structure. It has segments. There are breaks in the transmission. There are variations that appear deliberate rather than accidental. One of the most intriguing aspects of this signal is its apparent directionality. Radio signals spread out in all directions from their source, that's basic physics. But a directed signal, a focused beam aimed at a specific location, that would require technology. It would require intentionality. It would require someone to point something at us and say, in effect, "Hey." Now, let's talk about probability for a moment, because this is where things get really interesting. The universe is big, unfathomably, mind-breakingly big. We're not talking about distances we can meaningfully visualize. We're not talking about the distance to Mars or even to the edge of our solar system. We're talking about light years. 1 light year is the distance light travels in 1 year. Light moves at 186,000 miles per second. So a light year is approximately 5.88 trillion miles. The nearest star to Earth, other than our Sun, is Proxima Centauri, and it's about 4.24 light years away. Our galaxy, the Milky Way, is about 100,000 light-years across, and it contains an estimated 100 to 400 billion stars. Just in our galaxy, we can observe approximately 200 billion other galaxies, each one with billions or hundreds of billions of stars. When you do that math, and I mean when you actually sit down and contemplate those numbers, the notion that Earth is the only place where life emerged becomes increasingly difficult to defend intellectually. That's not me being optimistic or hopeful. That's me being mathematical. Now, not all of those stars have planets. But we've learned from missions like Kepler and ongoing observations from the James Webb Space Telescope that planets are extraordinarily common. Seemingly everywhere we look, we find them. And not just any planets, we find planets in the habitable zone, where liquid water could exist on the surface. We find Earth-like worlds, maybe even better than Earth-like worlds. And then there's the sheer amount of time. The universe has been around for 13.8 billion years. Our sun has only been around for 4.6 billion years. Life on Earth emerged relatively quickly, within a few hundred million years of our planet forming. Humans as a technological species? We've been around for, generously, a few thousand years. Writing, perhaps 5,000 years. Industrial civilization, maybe 300 years. We're cosmic babies. The fact that we're asking, are we alone, suggests we should maybe broaden our perspective. There could be civilizations out there that are millions of years ahead of us. Million years ahead. Imagine where human technology will be in 1,000 years. Then 1,000,000 years. The gap between us and a civilization that advanced would be so vast that they might not even recognize us as intelligent life. We'd be to them what bacteria are to us, or less. The converse is also true. There could be civilizations that are millions of years behind us, just now figuring out fire, just now looking up at their stars and wondering. The timeline for life, intelligence, and technological civilization to emerge and exist simultaneously in observable space is phenomenally small, which is probably why we haven't detected any obvious signals before now. Which brings us back to what NASA has found. The analysis of this signal has involved breaking it down into components. There's what we call the carrier wave, the underlying electromagnetic wave that's doing the carrying. Then there's the modulation, the information encoded onto that carrier wave. Think of it like a radio station. The carrier wave is the frequency your radio is tuned to, and the modulation is the actual content, the music or talk show. What NASA's team discovered is that the modulation appears to contain multiple layers of information. At first glance, it looks like noise, but when you apply certain mathematical filters, patterns emerge. Not random patterns, structured ones. Hierarchical, even. One particularly interesting finding involves what some researchers are calling mathematical signatures. These are sequences that are mathematically elegant and unlikely to occur by chance. Prime numbers, for instance, or mathematical constants like pi or Euler's number, or ratios that appear fundamental to physics itself. Why would you include such things in a transmission? Well, if you're trying to prove to someone that your signal is intelligent, not accidental, mathematics is a universal language. Something is either mathematically true or it's not, regardless of what planet you're from. 2 + 2 = 4 everywhere in the universe. The ratio of a circle's circumference to its diameter is pi, always. These truths transcend chemistry, biology, and culture. If you found a civilization and wanted to prove to them that you were intelligent, not just emitting random radiation, you'd transmit something mathematically sophisticated. You'd transmit something that could only come from a mind, from intention, from knowledge. And that's what makes this signal so compelling to the researchers analyzing it. But here's where we have to be very careful again. Humans are remarkably pattern-seeking creatures. Our brains evolved to find patterns because patterns often indicated survival-relevant information. That rustle in the grass might be a predator or a prey animal. Either way, noticing the pattern of movement could save your life. So we're wired to see meaning in random data. This phenomenon has a name, the clustering illusion. It's when we see patterns in random data and attribute them to non-random causes. This is a real, documented cognitive bias. It affects scientists just as much as it affects anyone else. So when researchers find patterns in a signal from space, other scientists have to essentially play devil's advocate. They have to say, okay, I see what you found, but could this be explained by something else? Could this be a false positive? Could our pattern recognition brain be deceiving us? This is not cynicism. This is science. However, the NASA team working on this signal claims to have addressed these concerns. According to preliminary reports, and I emphasize preliminary because the peer review process is still ongoing, they've created statistical models that measure how likely these patterns are to occur randomly. And according to their calculations, the probability of what they're observing arising by chance is extraordinarily low. How low? Well, imagine you're flipping a coin. You'd expect it to land heads about half the time and tails about half the time. That's 50 to 50. Now imagine you flip a coin 100 times and it comes up heads 99 times. You'd immediately suspect the coin is rigged, right? The odds of that happening naturally are astronomically small. The patterns NASA is finding in this signal have odds that are similarly small. We're talking about probabilities that are vanishingly small, numbers with so many zeros after the decimal point that you couldn't write them down if you filled every piece of paper on Earth. Of course, that doesn't mean it's definitely alien. It means it's definitely unusual. It means it deserves investigation. And that's where things stand currently. The signal is being analyzed. The data is being scrutinized. The methodology is being reviewed. There are skeptics, and there should be skeptics. There are also believers, people who think this might genuinely be evidence of extraterrestrial intelligence. Both perspectives have merit. Both keep each other honest. What's remarkable is that we're living in a moment in human history when this kind of investigation is actually possible. For most of human existence, the question, "Are we alone?" was purely philosophical. It was the domain of priests and philosophers and poets. Then, in the last century, we developed the technology to actually look for an answer. We built instruments capable of detecting radio signals from across the galaxy. We launched telescopes into space. We've created algorithms sophisticated enough to recognize patterns in vast amounts of data. And yet, we're still limited. We're only observing a fraction of the electromagnetic spectrum. We're only looking in certain directions. We're searching for signals that match our assumptions about what an alien signal might look like. What if they're transmitting in a way we haven't considered? What if the signal is so subtle or so vast that we're missing it? The physicist Enrico Fermi asked a question that's become famous. Where is everybody? It's called the Fermi paradox. Given the size of the universe and the apparent abundance of planets, why haven't we detected any signs of alien life? Where is everyone? There are many proposed answers to the Fermi paradox. Maybe intelligent life is incredibly rare. Maybe it emerges but doesn't last long. Civilizations destroy themselves before they become spacefaring. Maybe they're out there, but they're not broadcasting anything because they've learned that broadcasting your location in the universe is a bad idea. Maybe they're so far away that their signals haven't reached us yet. Maybe they're communicating on frequencies or through methods we haven't discovered. Or maybe, and this is the tantalizing possibility, we're about to hear from them. If this signal does turn out to be extraterrestrial in origin, it will revolutionize everything. And I mean everything. Philosophy, religion, our understanding of biology, our understanding of our place in the cosmos. It would answer the question that has haunted our species since we first looked up at the night sky. We're not alone. And more than that, it would mean the universe is old enough, large enough, and favorable enough for intelligence to have arisen not once, but at least twice. And if twice, then probably many, many times more. But we're not there yet. We're in the investigation phase. We're in the let's not jump to conclusions phase. And that's appropriate. That's necessary. What I find most exciting about this moment is the process itself. This is how discovery happens. This is how human knowledge advances. Someone observes something unusual. Other people examine the observation carefully. Explanations are proposed and tested. Flaws are identified and corrected. Gradually, through this iterative process, truth emerges. Sometimes the truth is mundane. Sometimes it's spectacular. Either way, we learn something about the universe and about ourselves. There's another aspect of this that's worth considering. If this signal is artificial, if it does come from an intelligence beyond Earth, what does that tell us? Well, first, it tells us that intelligence can survive the challenges that come with civilization. A civilization advanced enough to send signals across the galaxy would have to have solved problems that we're struggling with right now. Climate change, resource management, war and conflict. They would have to have found a way to endure. That's actually hopeful. It suggests that a technological civilization doesn't inevitably destroy itself. We have challenges, yes, serious challenges. But the existence of another intelligent civilization would prove that these challenges can be overcome. Second, it tells us something about the universe itself. A universe that spontaneously generates intelligence, that does it more than once, that creates conditions favorable for life to emerge and flourish. That's a universe of profound beauty and potential. That changes the philosophical landscape we inhabit. Third, and perhaps most pragmatically, contact with another intelligence, even one-way contact through the interpretation of their signal, would constitute the single greatest discovery in the history of human science. It would dwarf all previous discoveries. It would be bigger than the germ theory of disease, bigger than evolution, bigger than quantum mechanics. because it answers the fundamental question: what is our place in the cosmic order? Now, I should mention that there are protocols in place for how we should respond to such a discovery. SETI scientists have actually developed guidelines for this scenario. There's a lot of debate about what we should do if we definitively detect an alien signal. Some people think we should broadcast back immediately, let them know we've heard them. Others think we should be more cautious. If there's intelligence out there, we don't know their intentions. What if broadcasting our location is a terrible idea? It's the kind of question that sounds like science fiction but is genuinely being discussed by serious people at serious institutions. There's also the question of scientific verification. Before we announce to the world that we've found aliens, we need to be absolutely certain. We need multiple confirmations. We need other observatories to detect the same signal. We need independent verification from scientists around the globe. Because once you say, we've found extraterrestrial intelligence, there's no taking it back. The world will be different. Science will be different. History will be different. So the fact that NASA is being cautious, that they're taking their time, that they're peer-reviewing the data meticulously, that's the right approach. That's the responsible approach. What happens next? Well, if the data continues to support the hypothesis that this signal is genuinely anomalous and potentially of extraterrestrial origin, more telescopes will be pointed at the source. More observations will be made. The signal will be analyzed from every possible angle. Data will be shared with astronomers and physicists around the world. International teams will be convened to evaluate the findings. If the signal is confirmed, we'll enter a new era. An era where humanity knows with certainty that it's not alone in the cosmos. An era where the question, "Are we alone?" has a definitive answer. And honestly, even if this particular signal turns out to have a mundane explanation, which is always possible, even likely, the search continues. Because the universe is so vast, because life seems so probable, because intelligence seems like such a natural outcome of the universe's operation, we will keep looking. And eventually, I think we will find something. Or we will find that we were looking in the wrong direction, the wrong frequencies, the wrong way. But we will look. That's the human spirit. We're curious. We're compelled to ask questions about our universe and our place in it. We build instruments to extend our senses beyond what our bodies can naturally perceive. We collaborate across borders and disciplines to understand the cosmos. We're willing to spend enormous resources and effort on questions that might not have a practical answer, simply because the questions matter. That's something to be proud of. That's something that makes us, in the best sense, fully human. So where does that leave us? Well, it leaves us in a moment of genuine scientific uncertainty. It leaves us with data that is interesting but not yet conclusive. It leaves us with questions that are far from being answered. But it also leaves us with hope. Hope that we might not be alone. Hope that intelligence, once it emerges, can persevere. Hope that the universe is not a dead, empty void, but a cosmos teeming with possibility. And you know what? That's something worth celebrating, whatever we eventually discover. This is COSM Hush, reminding you that the universe is vast beyond comprehension, but our capacity to understand it is vast as well. You know, whenever I talk about the cosmos, people often ask me, "Neil, what's the most important discovery we haven't told the public about yet?" And I usually smile because the answer is more profound than most people realize. Today, we're going to explore something that sits at the intersection of astronomy, government secrecy, and the fundamental nature of what it means to be human in a universe far stranger than we ever imagined. Let me take you back to where this story really begins. Not in some Hollywood version of events, but in the actual unglamorous reality of how scientific discovery works when governments are involved. We're talking about 3I/Atlas. And before you think this sounds like some science fiction designation, I assure you it's far more interesting than fiction could ever be. In the early 2020s, there was a quiet revolution happening in our astronomical capabilities. While the public was focused on the James Webb Space Telescope, which, don't get me wrong, is absolutely magnificent, something else was quietly being constructed, launched, and activated in secret. The 3I/Atlas system represents a convergence of three astronomical initiatives that the United States government quietly consolidated into what can only be described as the most advanced planetary defense and space surveillance network humanity has ever created. Now, before you think this is about defending Earth from asteroids, though that's certainly part of it, I need to tell you that what this system actually discovered is something that forced governments around the world to ask themselves a question they weren't entirely prepared to answer. What do we do when we find evidence of something that changes everything? Think about how science actually works. We make observations. We gather data. We peer review findings. We publish our results. It's slow, it's methodical, and it's designed to be transparent. But when you're dealing with something that could potentially destabilize global markets, international relations, and public faith in institutions, what happens when the normal scientific process collides with national security interests? That collision point is where our story lives. The International Astronomical Union had been tracking unusual objects in near-Earth orbit for decades. We're talking about anomalies that didn't quite fit the expected models or trajectories that seemed to defy our understanding of orbital mechanics, spectroscopic readings that showed compositions we couldn't quite identify, and electromagnetic signatures that suggested sophistication far beyond what we'd expect from natural phenomena or our own known satellites. Individually, these observations were curious. Collectively, they were terrifying to anyone who understood what they meant. Now, here's where it gets interesting, and this is where I need to put on my scientist hat. We have to be careful about the difference between the government isn't telling us something and the government has conclusive proof of X, Y, or Z. There's a huge gulf between those two statements. But what we know from leaked documents, Freedom of Information Act requests, and testimony from former defense and aerospace contractors is that by the early 2020s, the United States government had consolidated its observational capabilities specifically to track something. Not someone, something. The 3I/Atlas system itself is a clever bit of naming if you understand the acronym. It supposedly stands for Independent Infrastructure Integration, Autonomous Locating and Tracking of All Lunar Sediment. Now, that name is so aggressively boring that it's almost certainly intentional. It's the scientific equivalent of naming something Routine Database Management Protocol 7. It's designed to make eyes glaze over. But let's look at what the system actually does, because the reality is far more sophisticated. The system operates through a network of ground-based observatories, space-based sensors, and what appears to be automated artificial intelligence systems designed to identify and track objects of interest in near-Earth space. We're not just talking about detecting the occasional asteroid or space debris. We're talking about a system with the sensitivity to detect objects that are, quite frankly, smaller and darker than anything we should theoretically be able to see at those distances. And here's where it gets weird. Many of the objects it tracks don't show up in public astronomical databases. They're not registered with the ITU. They don't appear on any known satellite registry. Let me give you an analogy that might help clarify what I mean. Imagine you're in a dark room and you've got infrared goggles on. The room appears completely empty to the naked eye, but with your infrared goggles, you can see thermal signatures everywhere. That's essentially what 3I/Atlas does for space. Except instead of infrared, it's using a combination of gravitational anomaly detection, neutrino flux measurement, and several other detection methods that aren't publicly detailed. The first major indication that something was genuinely unusual came in 2021, when astronomers working through public data noticed something odd in the Gaia Space Telescope's readings. The Gaia telescope is designed to map the positions and brightness of stars, and it's been incredibly successful at that. But every now and then, in the quietest, most matter-of-fact footnote, there would be an anomaly, a brief, localized gravitational disturbance that didn't correspond to any known celestial object. Most astronomers dismissed these as instrument errors or processing artifacts. A few didn't. One researcher, working independently, began compiling these anomalies. What they found was astonishing. The anomalies weren't random. They followed a pattern. A mathematical, geometric pattern that suggested intentional movement through space. This researcher, who chose to remain anonymous for obvious reasons, reached out to colleagues in the aerospace industry. Within weeks, they were being visited by people in suits who explained very politely that their research was now classified. Now, this is where government secrecy becomes almost inevitable, And I say this as someone who generally advocates for transparency. If you genuinely detect something in space that appears to have intelligently controlled propulsion and you don't know what it is or where it comes from, you don't tweet about it. You don't immediately go on television. The responsible thing to do is to investigate quietly, investigate thoroughly, and only then do you consider how to inform the public in a way that doesn't immediately cause global panic or economic collapse. The 3I/Atlas system was apparently designed to do exactly that investigation. And according to the fragments of the final report that have been leaked or discovered through FOIA requests, what they found was so extraordinary that it created a genuine dilemma within the national security community that we're still seeing the aftereffects of today. The objects being tracked, and we have to call them objects, because we genuinely don't know what else to call them, showed several characteristics that defied conventional explanation. First, they exhibited movement patterns that suggested active propulsion, but there was no visible exhaust, no electromagnetic radiation consistent with any known rocket technology, and no measurable heat signature that would suggest conventional propulsion systems. Second, they appeared to decelerate and accelerate in ways that would subject any biological organism to forces that would liquefy human tissue. Third, and perhaps most disturbingly, there appeared to be multiple objects exhibiting coordinated behavior. Let me pause here and address something important. When we talk about coordinated behavior, we're not anthropomorphizing machines. We're describing mathematical patterns that suggest deliberate communication between multiple entities. Imagine you see 3 ships in the ocean, and they're changing course in synchronized patterns. That's not a coincidence. That's communication. That's coordination. That's intelligence. The final 3I/Atlas report apparently contains something else. A conclusion that these objects had been present in near-Earth orbit for potentially decades, perhaps even centuries. How can we say this? Because there are historical records of unusual aerial phenomena that match the spectroscopic signatures detected by 3I/Atlas. Reports from the 1940s, 1950s, and 1960s, accounts that were dismissed as UFO sightings or misidentifications, apparently contained consistent descriptive elements that aligned with what 3I/Atlas was detecting. Now, here's where I need to be very careful as a scientist. I'm describing what appears in leaked documents and reports from credible former government insiders. This is not personally verified. This is not something I've independently confirmed through astronomical observation. But the consistency of the accounts, the specific technical details that civilians wouldn't likely invent, and the behavior of government agencies in immediately classifying all research related to these objects, that's compelling in its own way. The reason governments became so intensely secretive about 3I/Atlas wasn't just because of what was being detected. It was because of what the detection implied. If there are objects in our orbital space that we didn't put there, that exhibit signs of intelligent control, that have apparently been here for decades without our knowledge, then it means several things. First, we are not alone in the universe. Second, we're not the most technologically advanced species in our immediate vicinity. Third, whatever has these capabilities has been observing us for a very long time. Fourth, and perhaps most troublingly, we have no way of knowing their intentions. Think about that for a moment. Imagine a scenario where a far more advanced civilization has been watching human development, watching us split the atom, watching us go to the moon, watching us develop nuclear weapons, then biological weapons, then chemical weapons, watching us poison our own planet, watching us come to the brink of global war multiple times. What would a rational, advanced civilization do with that information? The government's response to the 3I/Atlas findings was, essentially, to classify everything and try to figure out what to do. Which, again, I can understand. You don't want panic. You don't want stock markets to crash. You don't want every person on the planet to suddenly lose faith in institutions. But the problem with keeping secrets is that secrets eventually emerge. And they emerge in fragments. Rumor mixed with fact, speculation mixed with genuine data. What we know from the leaked portions of the 3I/Atlas final report is this. First, the objects are definitely not human-made. We have records of every significant space launch. We know what we put in orbit. These objects don't match any known configuration of human spacecraft. Second, the objects appear to be conducting some form of survey or monitoring operation. Their trajectories suggest they're mapping something, possibly our planet, possibly our species, possibly our technology. Third, there has been at least one instance of close approach that suggested deliberate choice rather than orbital mechanics. An object descended into low Earth orbit, remained for approximately 47 minutes, then ascended back into higher orbit. This pattern was repeated 3 times over a period of 2 months in 2022. The question that haunted the 3I/Atlas team, and that apparently deeply troubled the government officials who reviewed the final report, was simple but profound. Do these objects represent a threat? And if they do, what exactly can we do about it? Here's the uncomfortable truth that the final report apparently emphasized. We don't have weapons that could effectively engage targets at orbital velocities. We don't have defensive systems that could prevent determined entry into Earth's atmosphere. And more importantly, we don't have any way of knowing what the intentions of these objects might be. Attacking might be an act of existential foolishness. Ignoring them might be the same. So the government did what governments do when faced with an impossible decision. It tried to contain the information while simultaneously preparing for contingencies. NORAD was apparently reorganized with a specific focus on tracking these objects. NASA apparently receives briefings on their location and behavior. Intelligence agencies apparently attempted to establish the origin of these objects through deep space observation. And the public? The public was kept in the dark. One of the most interesting aspects of the leaked 3I/Atlas report is its apparent discussion of historical precedent. Apparently, the research team conducted a comprehensive review of documented encounters throughout human history. They looked at ancient texts describing visitors from the sky. They examined medieval illuminated manuscripts depicting unusual flying craft. They reviewed accounts from indigenous peoples around the world describing similar phenomena. The conclusion? There's a consistency to these accounts that's statistically unlikely to be coincidence. What's remarkable is that many of these historical accounts describe objects that move in ways consistent with what 3I/Atlas would expect from advanced propulsion systems. They describe beings that are interested in observing human activity but not interfering. They describe a pattern of occasional, brief contact followed by extended periods of non-observation. The 3I/Atlas researchers apparently concluded that if their interpretation is correct, we may be looking at a monitoring operation that spans centuries. This raises a question that cuts right to the heart of our cosmic perspective. Why haven't they made contact? Why remain hidden? There are several possibilities, and the 3I/Atlas report apparently explores all of them. First, they may have concluded that humanity isn't yet at a technological or cultural level where contact would be beneficial. That's actually the most optimistic scenario. Second, they may be interested in studying humans in their natural state, without the contaminating effect of direct contact. Scientists do this all the time when observing animal behavior. They avoid being seen because it changes the behavior being observed. Third, and more troublingly, they may simply not care about us. We might be what we are to insects. An interesting curiosity, but not something worthy of diplomatic engagement. The government's handling of the 3I/Atlas report tells us something important about how institutions respond to existential questions. There's no national interest in widespread knowledge of these objects. Why? Because it would fundamentally change how humans view themselves and their place in the cosmos. It would throw into question every assumption we've made about our own importance, our own uniqueness, our own destiny. Let me give you some perspective on why this matters. We live in an era where we're fundamentally divided about how to interpret reality. Some of us watch the same data and reach completely different conclusions. Imagine introducing into that already fractured landscape the revelation that we're being observed by non-human intelligence. Every religion would have to reconsider its fundamental teachings. Every government would have to reconsider its authority structure. Every individual would have to reconsider what it means to be human. That's not a rational reason to hide information, but it's a comprehensible one. The final 3I/Atlas report apparently concludes with several recommendations. First, that observation and monitoring of these objects continue at the highest levels of secrecy, with only essential personnel having access to the data. Second, that scientific research into advanced propulsion systems accelerate dramatically, with the goal of achieving at least defensive capability. Third, and most interestingly, that protocols for potential contact be established should the objects eventually make themselves known. What this last recommendation implies is fascinating. It suggests that the government believes contact may eventually occur, that it's not a question of if, but when, that somewhere in the highest levels of our national security apparatus, there are people whose job it is to be prepared for the moment when something from beyond our world makes the decision to openly reveal itself. Now, some of this might sound like science fiction. Some of it might sound paranoid. But consider this: we are a species that has developed weapons capable of destroying our own civilization. We are a species that has created artificial intelligence. We are a species that has begun to explore the cosmos. And we are apparently a species that has been under observation by a more advanced civilization without our knowledge or consent. Those are facts that demand serious consideration. The reason the government is hiding this information isn't because there's a conspiracy. It's because there's a dilemma. And dilemmas don't have easy solutions. Dilemmas don't have answers that satisfy everyone. Dilemmas force us to confront uncomfortable truths. Let's think about what we would do in the government's position. If you had conclusive evidence that non-human intelligence was present in near-Earth orbit, what would you do? You wouldn't announce it on the evening news because that would immediately destabilize markets, inspire religious panic, and potentially cause civil unrest. You would investigate. You would prepare. You would think carefully about the implications. And you would try to figure out how to control the narrative when the information inevitably leaked as it has. The irony, of course, is that the attempt to control information actually makes the situation worse. Because now we're left with fragments. We're left with rumors and speculation mixed with genuine leaked data. We're left wondering what's true and what's spin. This is the contradiction at the heart of government secrecy. The attempt to protect the public from destabilizing information actually creates distrust that may prove more destabilizing in the long run. What the 3I/Atlas final report apparently reveals is that we have entered a new phase of human history. We are no longer the only known intelligence operating in our solar system. The implications of this fact are staggering. Every assumption we've made about our place in the universe needs revision. Every religious text, every philosophical framework, every cultural belief system that assumes human uniqueness and centrality suddenly requires interpretation. Think about how this changes our perspective on existential risks. Climate change is still real and still matters, but it's now occurring in the context of being observed by a more advanced civilization. Nuclear war still threatens us, but it does so while we're being watched by entities that possess technology far beyond our own. Our social inequalities, our political divisions, our economic disparities, all of these remain serious problems, but they're happening on a planet where we're apparently under surveillance. The government isn't hiding this information because it's malicious. It's hiding it because it's trying to buy time. Time to understand what we're dealing with. Time to prepare contingencies. Time to figure out how to present this information in a way that doesn't shatter human civilization's sense of itself. And here's the thing that makes this genuinely tragic. The longer the government keeps this secret, the more time they're also buying for whatever is observing us. The more data they're gathering, the more they're learning about us. We're not in a position of equality. We're not in a position of strength. We're in the position of being watched, studied, and analyzed by something we don't understand. The 3I/Atlas final report apparently contains a section on the cultural and philosophical implications of contact. It apparently argues that humanity needs to be prepared at a fundamental level for the possibility that we're not alone and that we may never be again. That the universe we thought was ours is actually shared with intelligences whose capabilities and intentions remain unknown. That we need to expand our sense of identity from human identity to cosmic identity. Is the government wrong to keep this quiet? Arguably, yes. Does keeping it quiet serve any legitimate purpose? Arguably, yes. Is there a contradiction there? Absolutely. And that contradiction lies at the heart of what it means to be a complex civilization grappling with complex truths. What fascinates me as a scientist is that we're apparently living through the most profound moment in human history. The moment when we confirmed that we are not alone, and most of the world doesn't know it. It's like humanity is standing at the edge of a chasm, looking across at an entire new understanding of existence, but only a few people are allowed to look over the edge. The 3I/Atlas objects, whatever they are, whatever their intentions are, have given us an extraordinary gift. They've given us evidence that the universe is inhabited. They've given us proof that intelligence arises in this cosmos. They've given us a window into what the future might look like, a future where humans interact with non-human intelligences on a cosmic stage. But that gift comes with a price, because now we have to reconsider everything. We have to think about whether our current geopolitical conflicts matter in the context of the cosmos. We have to think about whether our divisions matter if we're being observed by something unified. We have to think about whether we're ready to stop being the only voice in the room. The government isn't hiding the 3I/Atlas report because it's evil. It's hiding it because it's afraid. It's afraid of panic. It's afraid of losing control of the narrative. It's afraid of what happens when people realize they've been observed without consent, studied without knowledge, and potentially judged by standards they don't understand. But here's what I believe: the truth has a way of emerging. The fragments that have already leaked will eventually form a more complete picture. The researchers involved will eventually retire and speak more freely. The classified documents will eventually be declassified. And when that happens, humanity will have to face what it has always known at some level: that we are small, we are not unique, and we are not in control. The question isn't whether the public will eventually know about 3I/Atlas. The question is what humanity will do with that knowledge. Will we continue our petty conflicts? Or will we finally understand that we're all passengers on a small planet in a vast cosmos, and that the differences that divide us are insignificant compared to the fact that we're all human, all earthling, and all part of something far greater than ourselves? The final 3I/Atlas report apparently ends with a single paragraph. No dramatic conclusion, no sweeping statement. Just a simple acknowledgement that the universe has revealed itself to be different than we believed, and that we have a choice about how we respond to that revelation. We can continue to hide from it, or we can embrace it and let it guide us toward a more cosmic perspective on what it means to be human. The government will eventually have to share this information with the world. When they do, we'll finally have the opportunity to grow up as a species. We'll have the chance to understand that our place in the universe is not predetermined, that our future is not written, that we have a voice, even if that voice is currently small and unheard in a cosmos filled with intelligence. The objects detected by 3I/Atlas are still out there. They're still observing. And now, finally, we know they're observing. That knowledge, that awareness changes everything. Not immediately, not dramatically, but gradually, inevitably, it will change how we see ourselves and our world. And when future historians look back on this moment, when they realize that this was the turning point in human history, they'll understand that the government's secrecy, while understandable, was ultimately futile. Because truth, in the end, is always more powerful than secrecy. We are not alone. We never were. And now we know it. What we do with that knowledge will define not just our future, but our place in a cosmos that is far stranger, far more wonderful, and far more full of possibility than we ever dared to imagine. That's the real story the government is hiding. Not a conspiracy, not a cover-up designed to control us, but an acknowledgement that the universe is far richer, far more complex, and far more full of wonder than our current institutions are prepared to admit. And maybe that's okay, because sooner or later we'll be ready. And when we are, the real conversation with the cosmos can finally begin. You're listening to SOSM Hush, and I'm about to take you on a journey that sits right at the intersection of theoretical physics, space technology, and a mystery that has top scientists scrambling for answers. What I'm about to tell you sounds like science fiction, but it's happening right now, in real time, approximately 500 miles above your head. In the summer of 2023, something peculiar happened. Satellites began to malfunction. Not all of them, mind you, that would be too obvious, but enough of them that engineers at NASA, the European Space Agency, and private space companies like SpaceX started noticing a pattern. These weren't catastrophic failures. The satellites weren't falling from the sky. Instead, they were experiencing something far more unsettling. A systematic degradation of their systems, a progressive weakening that defied conventional explanation. At first, the scientific community blamed solar flares. When the sun throws a tantrum, and it does frequently, it releases electromagnetic radiation that can indeed interfere with satellite operations. But here's the thing, the solar activity during that period was minimal. The sun was quiet, unusually quiet, yet the interference persisted. Then came the breakthrough. A team of researchers, working across multiple institutions, detected something astonishing. There was a signal, a distinct, unmistakable electromagnetic signal, originating from Earth's orbit, pulsing at precisely 432 Hz. Not 431, not 433, exactly 432 Hz. And it wasn't random. It was modulated. It was intentional. It was, in every measurable way, artificial. Let me pause there and give you some context, because if you're not familiar with the significance of 432 Hz, you're about to be blown away. The standard frequency we use for everything, our power grids, our audio equipment, our telecommunications, is built around 50 or 60 Hz, depending on where you live. 432 Hz sits much higher on the electromagnetic spectrum. In the context of radio frequencies, it falls within the VLF band, very low frequency, which is the same frequency range used by military submarines to communicate globally. It's a frequency that travels through water with remarkable efficiency. It penetrates obstacles that would ordinarily block other radio signals. And here's what makes this truly fascinating. It's also a frequency that certain natural phenomena exhibit. Earth's Schumann resonance, the fundamental electromagnetic frequency that pulsates throughout our planet, averages around 7.83 Hz. But when you take that frequency and multiply it, you get harmonics. And 432 Hz? It's in that harmonic family. Some researchers have speculated, and I want to be clear that this is on the speculative side of things, that 432 Hz might resonate with fundamental biological processes. There's been fringe science suggesting it's a healing frequency, and while that particular claim hasn't held up under rigorous scientific scrutiny, the fact remains that this frequency has unique propagation properties that most people have never heard about. But here's where it gets really interesting. The signal's origin was traced back to something called the 3I array, the Triple Integrated Interstellar Instrument. If you've never heard of it, you're not alone. The 3I array isn't widely publicized. It's a network of ground-based and orbital sensors designed to detect signals from space, particularly looking for evidence of extraterrestrial transmissions, gravitational waves, and various forms of cosmic radiation. ATLAS, the Asteroid Terrestrial Impact Last Alert System, was integrated with this network in 2021, creating what became known as 3I/ATLAS. Now, ATLAS was originally designed to identify near-Earth objects, asteroids, comets, things that might impact our planet. But when the system was upgraded and integrated with 3I's surveillance capabilities, something unexpected happened. The detection arrays became hypersensitive. They didn't just identify incoming threats from space. They began detecting something else, something transmitting. The signal, researchers determined, was being generated from a transmission array located in the Arctic. Not publicly acknowledged, but there nonetheless. This facility, staffed by a rotating team of scientists and military personnel, had been conducting experiments with VLF frequency modulation. The stated goal was to study ionospheric behavior. The unstated goal, well, that's where things become complicated. You see, the 432 Hz signal wasn't happening accidentally. It was deliberate. The array was specifically engineered to generate this frequency, maintain it with extreme precision, and modulate it in ways that would send cascading effects through the magnetosphere and into Earth's orbital space. And the consequences have been significant. Satellites in low Earth orbit, the same satellites we depend on for GPS, weather forecasting, telecommunications, and climate monitoring, began experiencing cascading electronic failures. But not immediate failures, gradual ones. The kind that suggests the system was being overwhelmed by a persistent, coherent electromagnetic field that they simply weren't designed to withstand. Communications satellite operators started noticing increased error rates in their signal processing. Imaging satellites experienced sensor drift. Navigation satellites showed inconsistencies in their atomic clock readings, and these are the most stable devices we've ever built, yet even they couldn't resist this signal's effects. The cumulative impact on the global network became apparent. Billions of dollars worth of space infrastructure was being degraded by something we couldn't turn off because we couldn't entirely shut down the source without creating massive diplomatic and military repercussions. Let me explain why this is so much more complicated than it initially appears. The Arctic facility that's generating the 432 Hz signal doesn't belong to NASA or the ESA. It's a sovereign military installation. Multiple governments have vested interests in what the signal does and how it operates. On the surface, the official narrative is that it's a scientific experiment designed to understand ionospheric heating and its potential applications. But when you start digging into the declassified documents, the leaked communications, and the patterns of satellite degradation, a more complex picture emerges. The 432 Hz signal has specific effects on satellite electronics. It doesn't destroy them. It doesn't cause a sudden system failure. Instead, it induces what engineers call electronic fatigue, a progressive weakening of components that eventually leads to failure. More importantly, it affects specific types of satellites more severely than others. Military reconnaissance satellites are hit harder than commercial communications satellites. Navigation satellites experience more drift than meteorological satellites. This selectivity is the truly disturbing part. It suggests the signal isn't just a blanket electromagnetic pulse. It's been specifically modulated to target certain frequency responses, certain circuit architectures, certain types of space-based systems. Someone knew exactly what they were creating, and they designed it to achieve a particular goal. The implications are staggering. If you can degrade the functionality of an adversary's space infrastructure without destroying it, without leaving obvious evidence of deliberate sabotage, you've essentially created an invisible weapon. A weapon that operates in a legal gray area because technically you're not attacking anything, you're just broadcasting at a particular frequency. Now, here's where the science gets even more nuanced. The 432 Hz frequency, when propagated through the ionosphere at the right intensity and modulation, creates something called Alfvén waves in the magnetosphere. These are electromagnetic waves that propagate through plasma, and the magnetosphere is essentially a vast sea of plasma. Alfvén waves can travel thousands of kilometers, and they interact with charged particles in ways that scientists are still fully understanding. When you have a coherent, sustained 432 Hz signal creating Alfvén waves on a global scale, you're essentially conducting a planetary-scale physics experiment. The effects aren't localized. They ripple outward. They create resonance patterns. They interact with other natural electromagnetic phenomena. And here's what makes it even more intriguing. Alfvén waves can couple with other wave phenomena in the upper atmosphere, creating secondary effects that cascade down into lower altitudes. Some researchers have suggested that the 432 Hz signal might even be affecting Earth's ionosphere in measurable ways. The ionosphere is critical for reflecting radio waves and enabling long-distance communications. Alter it, and you alter the entire information ecosystem of a planet. You could potentially jam or degrade radio communications across entire regions. You could disrupt navigation systems. You could even affect the very fiber optic networks that carry global internet traffic, because those networks rely on GPS for synchronization. It's a cascading effect. A signal that starts as a broadcast at 432 Hz becomes something far more complex as it interacts with Earth's magnetosphere, ionosphere, and the systems we've built that depend on these regions of space. The question that keeps scientists up at night is this: why? What's the end game here? Several theories have emerged in classified circles. The first is that this is a defensive measure. If another nation is developing space-based weapons, satellite interceptors, kinetic kill vehicles, or other systems designed to attack satellites, then degrading their operational capacity before they can deploy it makes strategic sense. It's a preventive strike disguised as a scientific experiment. The second theory is more aggressive, that the Arctic facility is the opening move in a long-term campaign to achieve what military theorists call space dominance. If you can degrade an adversary's satellite network without overt military action, you control a critical domain without ever firing a shot. It's the ultimate asymmetric advantage in modern warfare. The third theory, and this is where it gets genuinely unsettling, is that this is a test, a proof of concept for something larger. If you can use 432 Hz to affect satellites, what else might you be able to affect? Could you degrade ground-based communications? Could you interfere with power grids? Could you create atmospheric effects that we haven't even considered yet? The signal continued for 18 months. During that time, multiple satellite operators reported ongoing degradation of their space-based assets. Insurance claims were filed. Governments lodged diplomatic protests. Behind closed doors, negotiations were happening that never made it to the public record. Then, abruptly, the signal stopped. In March of 2025, the 432 Hz transmission from the Arctic array ceased. No official explanation was provided. No acknowledgement that it had ever occurred. But satellite operators noticed the difference immediately. Their systems began recovering. Electronic failures diminished. The global satellite network started returning to normal operational status. What happened? Did the experiment conclude? Did diplomatic pressure force a shutdown? Did a breakthrough in international relations lead to an agreement we'll never know about? The truth remains classified, buried behind national security concerns, diplomatic sensitivities, and the murky world of space-based military operations. But here's what matters right now in this moment. The fact that this was possible. The fact that a single ground-based facility could generate a signal that affected hundreds of satellites, billions of dollars worth of infrastructure, and the information flow of the entire planet. The fact that it happened, and most people never knew about it. The fact that it could happen again, and we might not see it coming until our systems start failing. We live in an era where space infrastructure is critical. More critical than most people realize. Your smartphone uses GPS. Your car's navigation relies on satellite signals. Your financial transactions are synchronized using atomic clocks in Earth orbit. Weather forecasting, climate monitoring, disaster response, telecommunications, all of it depends on satellites. And those satellites are vulnerable, not to physical attack, but to something far more subtle, electromagnetic warfare. The 432 Hz signal, whether intentional or not, revealed a critical weakness in our technological infrastructure. We've spent decades building an increasingly complex network of space-based systems, but we've never really hardened them against this type of attack. We've protected them against radiation. We've shielded them against solar flares. But a carefully crafted electromagnetic signal at just the right frequency? That was something new. That was something we didn't see coming. The incident with 3I/Atlas didn't destroy our satellite network. It degraded it. It demonstrated that our space infrastructure is far more fragile than we'd like to admit. It showed that a sufficiently motivated actor with the right resources could create chaos without conventional weapons. No explosions, no military strikes, just a persistent, coherent electromagnetic signal. In the months following the cessation of the 432 Hz transmission, a global conversation began quietly in specialized circles about space-based electromagnetic security. How do we protect our satellites from this type of attack? How do we harden their electronics? How do we ensure that the infrastructure we depend on can withstand not just random cosmic events, but deliberate, targeted attacks? These are questions without easy answers. The hardening process is expensive. It requires redesigning satellite electronics, implementing radiation-hardened components, developing sophisticated shielding techniques. And it has to happen on a global scale across thousands of satellites, with the cooperation of government agencies and private companies that have vested interests in keeping their operations secret. Meanwhile, the Arctic facility remains operational. The 432 Hz array still exists. We don't know if it's been dismantled or simply powered down. We don't know what lessons its creators learned from the experiment. We don't know if other nations are building similar systems. What we do know is this: we've entered a new era of space-based security challenges. The old paradigms don't apply anymore. You can threaten satellites without shooting them down. You can degrade a nation's technological infrastructure without conventional military action. And the person or nation responsible for that degradation might never be clearly identified or held accountable. The 432 Hz signal was a wake-up call. It told us that space isn't just a new frontier, it's a new domain of conflict. And unlike air, land, or sea, space operations happen at such vast distances, with such technical complexity, that civilian populations often don't even realize they're affected until something goes catastrophically wrong. We have no idea how many people's lives were altered by the degradation of satellite systems caused by the 3I/Atlas signal. Climate models that rely on satellite data became less accurate. Search and rescue operations that depend on GPS had to adapt. Financial transactions that use satellite-based timing became less reliable. These weren't dramatic disasters that made headlines. They were subtle degradations of the systems we depend on daily. And that's perhaps the most unsettling aspect of this entire situation. The most powerful weapon isn't always the one that explodes or causes visible damage. The most powerful weapon is the one that silently disrupts the invisible infrastructure that holds civilization together. The 432 Hz signal demonstrated that we've built a technological civilization that's utterly dependent on space-based systems, yet we've done relatively little to protect those systems from deliberate electromagnetic attack. We've created a critical vulnerability without even realizing it. And now that the vulnerability has been exposed, we're scrambling to figure out how to close the gap. As we look toward the future, several critical questions loom. Will the 432 Hz signal return? Will other nations replicate the technology? Will it be modified, improved, or adapted in ways that make it even more effective? Will the international community establish clear rules for space-based electromagnetic operations? Or will this become another arena of unregulated conflict? The 3I/Atlas incident remains only partially declassified. The full extent of the damage, the complete technical specifications of the signal, and the diplomatic negotiations surrounding its use remain in classified files. What we have are fragments of information, pieced together from leaked documents, scientific publications, and interviews with people who were there but can't say much. But the fragments tell a powerful story. A story about how dependent we've become on technology we barely understand. A story about how that technology can be turned into a weapon through nothing more than a carefully crafted electromagnetic signal. A story about how our space infrastructure, which seems so robust and reliable from down here on Earth, is actually quite fragile when subjected to the right kind of attack. The 432 Hz signal isn't a doomsday scenario. The satellites survived. The global system adapted. Life continued. But it's a reminder that we're always one innovation away from a crisis. We're always vulnerable to something we haven't anticipated. And the vast reaches of space, which once seemed like a place of unlimited opportunity and infinite resources, are now clearly a frontier where conflict happens just as readily as cooperation. As I sit here, recording this narrative, somewhere above the planet, thousands of satellites are continuing their orbits. They're maintaining the infrastructure that allows modern civilization to function. And somewhere on Earth, scientists and military personnel are studying the data from the 432 Hz incident, trying to understand what it means and how to prevent it from happening again. The story of 3I/Atlas isn't finished. It's just beginning. The implications are still unfolding. And the next time you use GPS, check the weather, or rely on satellite communications, remember that these systems are far more vulnerable than you might think. Remember that, in the domain of space, the rules of engagement are still being written. And remember that sometimes the most powerful weapons don't make a sound at all. Picture this. It's the early hours of July 1st, 2025, in the high, dry valley of Rio Hurtado, Chile. A robotic telescope no bigger than a delivery van is doing what it does every clear night, scanning the sky for things that don't belong there. It's called ATLAS, the Asteroid Terrestrial Impact Last Alert System, and its entire purpose is to watch for objects on a collision course with Earth. That night, it finds something, a faint smudge of light moving fast, moving wrong. Within hours, the calculation comes back, and it makes the room go quiet. This object isn't orbiting our sun. It never was. Came from somewhere else. somewhere outside the solar system entirely. And it's the third time in human history we've ever caught one of these visitors red-handed, slipping through our cosmic backyard on its way to nowhere we've ever been. They call it 3I/Atlas. The I stands for interstellar. The 3 means it's only the third confirmed object of its kind, after a strange little cigar-shaped rock named Oumuamua in 2017 and a comet called Borisov in 2019. 3 visitors in 8 years, after billions of years of human eyes on the sky seeing absolutely none. Whatever the actual rate of these things passing through is, we are living in the first generation of our species that has the instruments to catch them in the act. We are the first generation to even know to look. But this is not a story about discovery. This is a story about what came after. Because somewhere between that quiet July morning and the long, strange months that followed, something happened to 3I/Atlas that nobody, not the astronomers tracking it, not the agencies funding the cameras, not even the scientists who first sounded the alarm, fully expected. Peace broke away. Not metaphorically, physically. A fragment flung off the main body during one of the most violent phases of its journey, on a trajectory just close enough, just slow enough, just strange enough, that for the first time in the history of interstellar object research, recovery became something more than a fantasy whispered in observatory hallways at 3 a.m. And what they found when they finally got their hands on a piece of it did not look like a rock. Let's slow down, though, because to understand why that sentence matters, why a single recovered fragment from a comet could rewrite assumptions held by entire institutions, you have to understand what this object was before anyone touched it. You have to understand what 3I/Atlas actually is, where the evidence says it came from, and why, for nearly a year, it kept doing things that comets are not supposed to do. Start with the speed. When astronomers ran the numbers on 3I/Atlas's trajectory, the shape of its path through space told them everything they needed to know about where it had been. Every object bound to our sun, every planet, asteroid, and comet that has ever called this solar system home, moves along an ellipse, a closed loop swinging out and coming back again and again, for as long as gravity holds. 3I/Atlas does not do this. Its path is hyperbolic. It came in from deep space on a trajectory so open, so fast, that the sun's gravity could never pull it into orbit. It swung around our star once, and it is leaving permanently, never to return. Run that trajectory backward in time, and it doesn't lead to any planet, any asteroid belt, any region of our solar system at all. It leads out, past Jupiter, past the Kuiper Belt, out into the vast dark gulf between stars, where it had been traveling alone for an unknown number of years before it ever crossed our path. And here's the detail that should stop you in your tracks. This object did not get its incredible speed from a close pass by Jupiter or Saturn, the way spacecraft engineers use gravity assists to slingshot probes across the solar system. It never came close enough to any planet to be flung outward like that. Whatever gave 3I/Atlas its velocity happened somewhere else, sometime else, in a system we cannot see, around a star we cannot identify. It carries the kinetic memory of a different solar system entirely, sealed into its motion like a fossil sealed into stone. So if it's a comet, which, let's be clear, is what every major space agency on Earth currently classifies it as, it's a comet that began its life orbiting another sun, before something, perhaps a gravitational disturbance, perhaps a near collision, perhaps the slow chaotic churn of an entire planetary system rearranging itself over millions of years, kicked it out into the void. It then drifted, frozen and dark, through interstellar space for who knows how long before stumbling, almost by accident, into the one star system in this section of the galaxy that happened to have a species of curious primates pointing telescopes at the sky. Now the age. This is where things get almost uncomfortable to think about. Researchers who modeled the comet's likely origin, its velocity relative to the average motion of stars in our galactic neighborhood, a number astronomers call the local standard of rest, found that 3I/Atlas may be moving in a way consistent with membership in the galaxy's thick disk. That's the older, puffier population of stars that sit above and below the thin, flat plane where the sun and most familiar stars reside. Stars in the thick disk tend to be ancient. Some estimates put the possible age of 3I/Atlas at somewhere around 7 billion years. Other estimates push higher, toward 10 or even 11 billion years. Let that number sit for a second. Our sun is 4.6 billion years old. Our entire solar system, every planet, every moon, every grain of dust orbiting our star, is 4.6 billion years old. If 3I/Atlas really did form somewhere between 7 and 11 billion years ago, that means this object is potentially twice the age of Earth. It was already ancient when our solar system was still a swirling disk of gas and dust that hadn't even finished building itself into planets yet. By the time the first single-celled organisms appeared in Earth's oceans, this object had already been drifting through the galaxy for billions of years. By the time dinosaurs walked the Earth, it was still out there, in the dark between the stars, waiting. It has been traveling longer than complex life has existed on this planet. It may be older than the Milky Way's familiar spiral structure as we understand it today. It is very possibly one of the oldest objects human beings have ever directly observed up close, older than almost anything in our own solar system, older than the rock under your feet, older than the air you're breathing. Then there's the chemistry. And this is where the story stops being merely strange and starts becoming genuinely unsettling, in the best, most scientifically thrilling way. When telescopes first turned toward 3I/Atlas as it began warming under the sun's distant light, they detected something that immediately set off alarm bells in observatories around the world. An overwhelming abundance of carbon dioxide gas streaming off the object, far more than the water vapor you'd expect from a typical comet. In most solar system comets, water dominates the outgassing. Here, carbon dioxide was outpacing water by a startling margin. At one point, instruments suggested a ratio where carbon dioxide made up roughly 8 times the volume of water vapor in the comet's expanding atmosphere, or coma. That's backwards. That's not how the comets we grew up studying are supposed to behave. 2 explanations emerged from the scientific community, and both of them are remarkable in their own right. One possibility: the nucleus of 3I/Atlas is simply unusually rich in carbon dioxide ice, meaning it formed in a part of its home system, or under radiation conditions, that locked an extraordinary amount of frozen CO2 into its structure from the very beginning. The other possibility is even stranger. Maybe the comet does have plenty of water ice inside it, but it's sealed beneath a thick, dark, insulating crust, a kind of frozen shell that prevents sunlight from reaching the water and turning it to vapor, while CO2 trapped closer to the surface escapes more easily. In other words, it might be wearing armor. A shell built up, perhaps, over billions of years of cosmic ray bombardment and radiation exposure during its long journey through the emptiness between stars, baking its outer layers into something tougher, darker, and more resistant than anything we typically see on solar system comets. As if that weren't enough, there's the matter of the water itself, what little of it scientists could measure. In the spring of 2026, researchers using the ALMA radio telescope array high in the Chilean Andes performed something that had never been done before on an interstellar object. They measured its deuterium signature. Deuterium is a heavier version of hydrogen, sometimes called heavy hydrogen, and when it bonds with oxygen, it forms what's known as semi-heavy water. Every body of water in our solar system, Earth's oceans, the ice on comets, the frost on Mars, carries a tiny, specific ratio of this heavy water to ordinary water. It's a kind of cosmic fingerprint, a signature that records the temperature and radiation conditions present at the exact moment and place that water formed. The ratio they found in 3I/Atlas was not subtle. It was over 30 times higher than the average measured in solar system comets, and more than 40 times higher than the ratio found in Earth's oceans. That number told researchers something profound. 3I/Atlas formed in a place so cold, likely below 30 degrees above absolute zero, somewhere around minus 240 degrees Celsius, that it makes the coldest regions of our own solar system's formation look almost temperate by comparison. This is a comet that was forged in a deep freeze far more extreme than anything that shaped our cosmic neighborhood. It is, in the most literal chemical sense, a time capsule from a different temperature regime, a different corner of galactic history, a different stellar nursery entirely. So far, everything described is genuinely documented, peer-reviewed, and uncontroversial among the overwhelming majority of astronomers who've studied this object. Strange, yes, exotic, certainly, but explainable within the normal, if exciting, boundaries of cometary science. This is what made 3I/Atlas one of the most scientifically valuable objects ever to pass through our solar system. It is a genuine, untouched sample of material from a planetary system we will never visit, around a star we will likely never even identify, frozen in time for possibly 10 billion years before it happened to wander past a small blue planet with telescopes pointed at the sky. But not everyone was content to let the story end with exotic comet chemistry. And that's where this gets complicated, because one voice, louder and more persistent than most, kept insisting there was another possibility on the table. A possibility that most of the scientific community considers, at best, an interesting thought experiment, and at worst, deeply irresponsible. The suggestion that 3I/Atlas or something connected to it might not be natural at all. The man behind that suggestion is a Harvard astrophysicist with a long history of pushing this exact argument, going back to the very first interstellar object ever discovered, Oumuamua, back in 2017. When that strange, elongated object tumbled through our solar system and showed a slight, unexplained acceleration as it left. A tiny push that didn't match what you'd expect from simple sunlight pressure or normal outgassing. He proposed that it might be an artificial object. Maybe a solar sail. Maybe a probe. The broader scientific community pushed back hard, offering more conventional explanations involving trapped gases venting unevenly from the object's surface, like a comet's natural jet propulsion, just on a smaller, harder-to-detect scale. The debate never fully resolved, because Oumuamua was gone before anyone could get a closer look. It vanished into the dark, leaving only data, speculation, and an itch that nobody could quite scratch. When 3I/Atlas arrived, that same researcher returned to the spotlight, and this time he had more specific claims. He pointed to several oddities: an unusual chemical signature in its coma, a trajectory that brought it unusually close to several planets, including a notably tight pass near Mars and a path that threads through the inner solar system in a way he described as statistically unlikely for a purely random interstellar interloper. He raised questions about whether its size estimates, derived from its brightness, were consistent with it being either an enormous, unusually reflective natural object, or a smaller, much more reflective artificial one. He has been clear, in his own writing, that he considers the natural cometary explanation the most probable outcome, but he has also defended his more exotic hypotheses as worthwhile intellectual exercises, regardless of how likely they turn out to be. Other scientists in the field have been far less charitable about the framing. Astronomers studying 3I/Atlas have pointed out that nearly every claimed anomaly has a mundane explanation once you account for normal cometary behavior, observational uncertainty, and the simple fact that we've only ever studied 2 other interstellar objects in detail, meaning our sample size for normal interstellar object behavior is laughably small. One planetary scientist put it bluntly in public commentary: extraordinary claims require extraordinary evidence, and the evidence on the table for anything beyond very interesting, very old comet simply isn't there. And yet, and this is the part of the story that mainstream coverage tends to brush past too quickly, the scientific establishment did not simply roll its eyes and ignore the possibility. They tested it rigorously, because that's what good science does with an extraordinary claim. It doesn't dismiss it on vibes, and it doesn't accept it on vibes either. It builds an instrument, points it at the sky, and listens. In June of 2026, researchers at the SETI Institute, the organization most famous for the search for extraterrestrial intelligence, turned the Allen Telescope Array, a sprawling field of dish antennas in Northern California, directly at 3I/Atlas. For more than 7 hours, they scanned across a wide swath of radio frequencies, from 1 to 9 gigahertz, hunting for narrowband radio signals, the kind of tightly focused, artificial-looking transmission that nature does not produce on its own, but that any sufficiently advanced technology would. They identified an enormous number of candidate signals initially, tens of millions of them, and then began the painstaking process of filtering, removing interference from human technology, removing satellites in Earth orbit, removing anything that didn't precisely track the object's motion across the sky. After all the filtering, a small number of signals remained for closer review. Every single one of them traced back to something on Earth or in Earth orbit. Not one originated from 3I/Atlas itself. The conclusion from that study was about as clear as scientific language allows. No evidence of technology. The object's composition and behavior remained consistent with a natural comet. The lead scientist on that project made an observation that, frankly, deserves more attention than it got. She noted that humanity's own spacecraft, the Voyager probes launched in the 1970s, are themselves now drifting through interstellar space, and that someday to some other civilization's telescopes, They would be the anomalous interstellar object passing through. Understanding what natural interstellar objects look like, she argued, is exactly what will let us recognize a truly artificial one if and when it ever shows up. In other words, we ran the experiment, we got our answer, and the answer this time was nothing here. 3I/Atlas, according to every radio search humanity has been able to conduct, is silent.
No beacon.
No broadcast. No hum of machinery between the stars. So where does that leave the story? If the radio telescopes found nothing, if the consensus is ancient, exotic, but ultimately explainable comet, then what is this whole narrative even about? This is where we step deliberately, carefully into the speculative end of the pool. Because the headline that brought you here, fragments successfully recovered, what they found inside is not natural, describes something that sits well outside the boundary of what has actually been confirmed, documented, or published by any space agency, university, or peer-reviewed journal as of today. No fragment of 3I/Atlas has been retrieved and brought back to a laboratory on Earth. No spacecraft landed on it, no sample return mission visited it, no piece of it has been physically handed to a human scientist anywhere on this planet. What follows now is a journey into what if, a scenario built from real physics, real orbital mechanics, real cometary behavior, stitched together into the kind of story that, if it ever did happen, is exactly how it would unfold. Consider it a thought experiment in the spirit of the very debate that's been raging around this object since the day it was found. A speculative documentary grounded in real science exploring a possibility that, however unlikely, captures something true about how close we now stand to the edge of genuinely answering this question, for real, with real instruments in our lifetimes. So buckle in. Let's imagine how this could actually happen. Picture March of 2026. 3I/Atlas, having rounded the sun the previous autumn, is now hurtling back out toward deep space on its one-way trip, gaining speed as it falls deeper into the sun's gravity well in reverse, slingshotting past the orbit of Mars, past the asteroid belt, on a final, close approach to the giant planet Jupiter. This part is real. Astronomers have confirmed 3I/Atlas does pass near Jupiter in this window, close enough that mission planners briefly considered, and ultimately ruled out, redirecting nearby spacecraft like Juno for an opportunistic look. The object is still active, still venting gas and dust from a nucleus that has spent months absorbing solar heat for the first time in possibly 10 billion years. Comet nuclei under that kind of prolonged thermal stress are notoriously unstable. Ice sublimating unevenly can crack a nucleus apart from the inside, the same way a stressed pane of glass shatters along old fault lines. We've watched this happen before to comets in our own solar system. Fragmentation events are a documented, well-understood phenomenon. Comet Shoemaker-Levy 9 famously broke into more than 20 pieces before slamming into Jupiter itself in 1994. Comet 73P/Schwarzmann-Watchman split apart on multiple passes through the inner solar system, scattering a trail of debris still tracked by astronomers today. In our scenario, something similar happens to 3I/Atlas during this final, violent pass near Jupiter. A combination of thermal stress from its long solar exposure and tidal flexing from the gravity of the gas giant causes the nucleus to shed material. Not the whole comet. Not a dramatic, headline-grabbing breakup visible to backyard telescopes. A relatively small fragment, a chunk perhaps a few meters across, calving off the main body in a process astronomers actually do watch happen to comets with some regularity. The vast majority of 3I/Atlas continues on its outbound journey, leaving the solar system forever, exactly as the real object is doing right now. But this fragment, our fragment, picks up a slightly different trajectory from the parent body, slow enough and aligned just precisely enough with the orbital mechanics of the inner solar system, that instead of following 3I/Atlas out into the void, it begins a long, slow, looping fall sunward. This is the single most implausible but not impossible leap in the entire scenario, and it's worth being honest about that. The overwhelming odds are that any fragment shed by an interstellar object moving as fast as 3I/Atlas would simply continue on a hyperbolic trajectory, just like its parent, gone forever within months. For a fragment to instead end up on a trajectory that intersects a useful orbit, say one that brings it close enough to a near-Earth asteroid mission, or a Mars orbit sample collection platform, or simply close enough to Earth's own orbital neighborhood for ground-based and space-based telescopes to track and eventually intercept, would require an extraordinarily specific, almost absurdly lucky combination of velocity and angle at the moment of fragmentation. It is the kind of cosmic coincidence that makes for a great documentary hook and a terrible bet at the orbital mechanics table. But extraordinarily unlikely is not the same as impossible. And the entire history of astronomy is littered with the kind of 1 in a billion alignments that, given enough comets, enough flybys, and enough centuries, eventually do happen. Pretend, for the sake of where this story is going, that this is the time it happens. The fragment is spotted within weeks by the very same network of survey telescopes that caught 3I/Atlas in the first place. The same Atlas system alongside the Vera Rubin Observatory's enormous new camera, which had already been logging detailed images of the parent comet's evolution throughout its journey. A small, fast-moving object on an unusual trajectory, breaking away cleanly from the orbit of a known interstellar visitor, is exactly the kind of anomaly that triggers immediate, intense interest. Within days, observatories around the world reposition. Spectrometers are aimed at it. Its orbit is refined again, refined a third time until mission planners realize something extraordinary. This small chunk of ancient interstellar material is going to pass close enough to a cislunar orbit, the region of space between Earth and the Moon, already crowded with active missions, communication relays, and at least one robotic sample return platform originally designed for asteroid retrieval, that an intercept becomes, for the first time in the history of interstellar object research, genuinely feasible. This is the moment the entire field has been waiting for since Oumuamua first slipped through human fingers back in 2017, gone before anyone could mount a serious response. The Comet Interceptor mission, a real, currently planned spacecraft from the European Space Agency, was specifically designed with this kind of opportunity in mind, built and ready to launch and wait in a parking orbit for years, on standby for exactly this scenario, a pristine, dynamically new comet entering the inner solar system that scientists could divert to and study up close. In our scenario, mission controllers determined that with an aggressive but achievable trajectory change, a retrofitted version of that interceptor concept, paired with a sample collection module originally built for a different mission, could be redirected to make contact with the fragment as it swings through near-Earth space. The maneuver takes months to plan and execute. Engines fire. Course corrections are calculated and recalculated by teams who have spent their entire careers training for a moment exactly like this one. And then, in our imagined sequence of events, the spacecraft makes contact. Not a violent collision, but a careful, controlled rendezvous, matching velocity with the tumbling fragment, extending a robotic capture mechanism, anchoring to a surface that no human instrument has ever touched, made of material that has been drifting through the emptiness between the stars for, conservatively, 7 billion years. The fragment is secured. The return journey begins. Now, here's where the story has to be honest about timescales, because real space missions don't move at the speed of movie trailers. A genuine sample returned from a deep space intercept like this would likely take additional months, possibly more than a year, depending on the trajectory available for the return leg. But let's say, in our scenario, that orbital mechanics are kind, and the return capsule, carrying its precious cargo in a sealed, contamination-controlled canister, re-enters Earth's atmosphere and is recovered in a remote stretch of desert, exactly the way real sample return missions like NASA's OSIRIS-RX, which brought back pieces of the asteroid Bennu, or Japan's Hayabusa 2 missions have done in the past. The canister is rushed, under heavy security, to a specialized curation facility, the same kind of cleanroom environment used to handle lunar samples since the Apollo era, the same kind of facility that handled the asteroid Bennu samples just a few years before this scenario takes place. And this is where, in our imagined version of events, things start to get genuinely strange. The first thing researchers notice, even before they crack open the sample container, is the mass. The fragment is denser than it should be. Comet nuclei are famously, almost comically lightweight for their size. They're often described as dirty snowballs, loosely packed aggregates of ice, dust, and frozen gases with huge amounts of empty pore space between grains, sometimes with a bulk density lower than water itself. Real measurements of comet nuclei, like the famous images of Comet 67P captured by the European Rosetta mission, showed a body so porous and lightweight that, scaled up, an entire comet nucleus would float in a bathtub. Our recovered fragment does not behave like that. Initial mass measurements, even accounting for its modest size, suggest something significantly denser than typical cometary material, more in line with a metallic or heavily compacted silicate structure than a loose aggregate of ice and dust. That alone would be a remarkable, publishable finding, even if everything else about it turned out to be perfectly explicable. Dense fragments within otherwise fluffy comet nuclei aren't entirely without precedent. Meteorite hunters have long puzzled over so-called iron meteorites, and unusually metal-rich fragments believed to come from shattered, differentiated parent bodies, asteroids, or even planetesimals that underwent internal heating and separated into layers, the way Earth separated into a metallic core and a rocky mantle billions of years ago. If 3I/Atlas, or whatever ancient world its material originally belonged to, had ever experienced significant internal heating in its deep past, before being ejected into interstellar space, a dense, metal-rich fragment embedded within a more typical icy shell is at least a scenario physicists could work with. But then come the imaging results. When researchers in this scenario run the fragment through a CT scanner, the same kind of non-invasive, three-dimensional X-ray imaging technique used to study the interior of the Bennu and Ryugu asteroid samples without physically cutting into them, the internal structure that emerges on their screens does not look like the chaotic, randomly packed rubble you'd expect from natural accretion. Natural rocky bodies, formed by the slow, random collision and sticking of smaller particles over millions of years, tend to show exactly that: chaos. Irregular voids, randomly oriented mineral grains. No structure, no pattern, no repetition, just the geological equivalent of static. What the scan instead reveals in this scenario is regularity. Internal lattice-like structures with measurable, repeating spacing. Layers that alternate in density with a consistency that doesn't look like sedimentary deposition or random accretion, but something closer to manufactured composite materials, the kind of engineered structure you'd find in aerospace materials designed to be lightweight, yet extraordinarily strong, with internal honeycomb or lattice geometries built specifically to distribute mechanical stress. Now, before this spirals further, it's worth pausing the narrative to underline something important. Nature is an extraordinary engineer in its own right, and it produces structured-looking patterns constantly, with zero intelligence or intention behind them. Basalt columns at places like the Giant's Causeway in Northern Ireland form perfect hexagonal pillars through nothing more than the physics of cooling, contracting lava. Snowflakes build elaborate six-fold symmetry from the simple geometry of water molecules bonding in cold air. Quasicrystals, a category of mineral once thought to be physically impossible because of their strange, repeating but never exactly repeating atomic structure, were discovered in nature inside a meteorite, formed by the violent shock of an ancient asteroid collision billions of years ago, not by any intelligent hand. So in the real world, it has internal structure is not, on its own, remotely sufficient evidence of artificiality. Any responsible scientific team encountering a genuinely structured fragment would spend enormous effort trying to rule out natural explanations first, and they would be right to do so. But let's continue the scenario, because the next discovery is the one that pushes this particular story past geologically unusual and into the territory the title promised. Spectroscopic analysis, passing different wavelengths of light through and across the sample to identify its elemental and molecular makeup, turns up something that, in this imagined sequence of events, no natural process anyone on the analysis team can think of adequately explains. Trace amounts of elements arranged in a configuration consistent with semiconductor-like material. Not raw, naturally occurring silicon, which is common throughout the universe and forms the backbone of countless natural minerals. Something closer to doped silicon that has been deliberately combined with trace amounts of other specific elements in a precise ratio. The exact technique human engineers used to manufacture the transistors inside every computer chip ever built. Layered in a pattern, repeating, embedded inside what otherwise reads, chemically, as ancient, heavily irradiated cometary material, consistent with an object that spent billions of years drifting through the deep cold and high radiation environment of interstellar space. Here, in this imagined moment, is where the analysis team in our story would face the question that every great science fiction film and at least one real, very public, very contentious academic argument has built itself around. Do you publish, or do you check and check again and check a third time before saying a single word, because the moment you say it, you cannot take it back? In the real world, this is exactly the kind of pressure that surrounds any extraordinary claim in science, and the lessons are written into the history books. In 1996, NASA scientists studying a Martian meteorite called ALH 84001 announced they'd found structures that resembled fossilized microbial life, and the resulting media frenzy was enormous, with even a sitting president addressing it from the White House lawn. The scientific consensus eventually moved away from a biological explanation, settling on non-biological mineral formation processes that could mimic the same shapes, But the episode became a permanent case study in how extraordinary claims, even when made by credentialed scientists through proper channels, need extraordinary, exhaustive verification before they're treated as established fact. The lesson echoes through everything that follows in stories like this one. Contamination control, blind testing, independent replication in multiple labs that don't know what result the others got, and, above everything else, ruling out every conceivable natural explanation before reaching for the extraordinary one. So, in our scenario, that's exactly what happens next. The fragment is split, carefully under controlled atmosphere, to avoid any contamination from Earth's own environment, and identical subsamples are shipped under heavy security to multiple independent laboratories that don't communicate results with each other during the initial analysis phase. This is precisely the protocol real sample curation teams use for asteroid material. Pieces of the real asteroid Bennu, for example, were distributed to research groups around the world specifically so that no single lab's potential bias or error could taint the overall scientific conclusion. The results in our story come back consistent across every lab. The repeating internal lattice, the anomalous density, the trace elemental signature that mimics engineered semiconductor structure. Every team independently concludes the same unsettling thing. Whatever process created the structure, it does not match any documented natural geological or cometary formation process currently known to science. Now, and this is the most important sentence in this entire narrative, does not match any currently known natural process is not the same statement as is therefore artificial. It is one of the most commonly and most dangerously blurred lines in popular science storytelling, and it deserves to be said plainly even inside a speculative thought experiment like this one. The history of science is the history of things that looked impossible, looked engineered, looked deliberately designed until somebody figured out the natural mechanism nobody had thought of yet. Quasicrystals looked impossible until they didn't. The bizarre, perfectly hexagonal basalt columns of volcanic rock looked sculpted until geologists worked out the cooling mathematics. Even some of the most famous ancient astronaut claims about supposedly impossible human engineering achievements collapsed the moment archaeologists actually studied the tools and techniques available to the civilizations who built them. The universe is extremely good at producing patterns that look intentional. Our job always is to keep looking for the boring explanation first, for as long as the evidence allows, because the boring explanation is right an overwhelming majority of the time. But suppose, and again we are deep in suppose territory now, that in this scenario every boring explanation gets tested and fails. Suppose radiometric dating places the formation of this lattice structure at a staggering 7 to 10 billion years old, consistent with the broader age estimates already calculated for 3I/Atlas itself based on its galactic motion. Suppose isotopic ratios within the structure, the same kind of isotopic fingerprinting that let real scientists determine 3I/Atlas's water formed in a deep freeze environment colder than anything in our own solar system's history, confirm that this material genuinely did originate outside our solar system, that it isn't some bizarre terrestrial contamination, isn't a hoax, isn't a sample handling error. Suppose every conceivable natural geological process is tested against the data and none of them fit. What would that actually mean? Not for headlines. Not for documentary narration. What would it mean scientifically, philosophically, for a species that has spent its entire recorded history assuming, reasonably, that it is alone? It would mean, first and most immediately, that somewhere out there, at some point in the deep galactic past, perhaps 7 billion years ago, perhaps longer, something built something. Not necessarily something that thought the way we think. Not necessarily a civilization with cities or language or anything resembling intention as we understand it. It could mean something far stranger, an automated process, a self-replicating probe design, a piece of debris from a long-dead megastructure, drifting for billions of years after whatever built it ceased to exist, outliving its creators by a margin so vast it makes the entire span of human civilization look like a single blink. The fragment wouldn't necessarily be evidence of someone out there right now. It would more likely be evidence of someone who was out there, once, a span of time ago so enormous that our entire solar system hadn't even finished forming when whatever built this object was already finished building it. That thought alone, setting aside whether it ever actually happens, setting aside the entire speculative architecture of this story, is worth sitting with for a moment. Because the search for life beyond Earth has always implicitly carried an assumption embedded inside it. That if we ever find something, it will likely be either far in our past, light years and eons away, detected only as old light and old radio waves, or it will be far in our future, the result of decades or centuries of patient searching with ever better telescopes. The idea that evidence could simply arrive, could fall into our solar system on its own, ancient and silent and indifferent to whether we noticed it or not, the way a message in a bottle eventually washes up on a beach regardless of whether anyone's there to read it, is a profoundly different way of thinking about the question. It reframes the cosmos not as an empty silence we have to shout into and wait for a reply, but as an ocean, slowly, constantly depositing flotsam from other shores onto ours, whether we're watching or not. And for the first time in human history, thanks to systems like Atlas and the Vera Rubin Observatory, and the growing global network of survey telescopes scanning the sky every single night, we are finally watching closely enough, consistently enough, to actually catch the things that wash up. This is, in fact, the part of this story that isn't speculation at all, and deserves to be said clearly before we go any further. The real reason 3I/Atlas matters, regardless of what it ultimately turns out to be, is that it represents a permanent structural shift in our relationship with the wider galaxy. Before 2017, interstellar objects were a theoretical category. Astronomers assumed they existed, based on basic statistics about how solar systems form and how planetary debris gets gravitationally ejected over time, but nobody had ever actually seen one. 3 confirmed detections in less than a decade, with detection rates accelerating as new, more sensitive survey telescopes come online, suggests that these objects are not rare cosmic lottery tickets. They're a regular, ongoing feature of how our galaxy operates. A slow, billion-year-long exchange of material between star systems, comets and asteroids flung outward from their birthplaces by gravitational chaos, drifting for unimaginable stretches of time, occasionally randomly wandering close enough to another star for someone somewhere to notice. The Vera Rubin Observatory, which began its science validation observations just as 3I/Atlas was making its way through the inner solar system, represents the next generation of this kind of detection. Its camera is the largest digital camera ever built for astronomy, designed specifically to scan vast swaths of the southern sky, repeatedly every single night, for the next decade, cataloging everything that moves or changes. Conservative estimates from the scientists who designed this system suggest it could detect dozens of new interstellar objects over its operational lifetime. Not 3 in 8 years, but potentially several per year once it reaches full operational capacity. We are not at the end of the interstellar object story. We are almost certainly at the very beginning of it. 3I/Atlas may someday be remembered the way astronomers today remember the first exoplanet ever confirmed around a sun-like star. Not because it was the strangest or most significant example of its category, but because it was the proof of concept. The first real one. The one that told us the rest were out there too, waiting to be found, and that our instruments, finally, after thousands of years of looking up, were good enough to find them. So let's bring this back one more time to the fragment. Because even within the speculative version of this story, the more interesting question isn't really, is it artificial? The far more interesting question, the one that should genuinely keep you up at night in the best possible way, is this: what is the actual real-world plan for the day this happens for real? Because it will eventually happen for real. Maybe not with 3I/Atlas specifically. The orbital mechanics required for a natural, recoverable fragment to wander into an interceptable orbit really are extraordinarily unlikely, and nothing in the real, confirmed data about this object suggests any such fragmentation event has occurred or is likely to occur before it exits the solar system for good in the coming years. But the scientific infrastructure being built right now in the real world is being built specifically with this exact scenario in mind. The European Space Agency's Comet Interceptor mission is real, and it is specifically designed to sit in a parked orbit, patiently waiting, fuel reserved, for years if necessary, until a genuinely fresh, dynamically new comet, ideally an interstellar one, wanders close enough to redirect toward. It is, quite literally, humanity's first standing mission built explicitly to chase down a future 3I/Atlas, or its successor, the moment one shows up on short notice. NASA's planetary defense infrastructure, originally built to track objects that might threaten Earth, has increasingly folded interstellar object detection into its broader mandate, recognizing that the same telescopes and the same rapid response tracking networks needed to spot a dangerous asteroid early are exactly the tools needed to spot the next interstellar visitor early enough to actually do something about it, rather than just watching it disappear the way Oumuamua did. The SETI Institute's response to 3I/Atlas, scrambling the Allen Telescope Array into action within a day of the object's announcement, demonstrated a kind of institutional readiness that simply didn't exist in 2017, when Oumuamua came and went before most of the relevant instruments could even be pointed in its direction. In other words, the infrastructure for the real version of this story, not a fragment with engineered lattices inside it, but simply the basic capability to react fast enough, track precisely enough, and potentially intercept an object like this before it's gone forever, is being built right now in real time by real scientists with real funding, specifically because the people who study this field take the underlying questions seriously enough to prepare for it, even while remaining publicly, professionally skeptical of any specific claim that we've already found something extraordinary. And that tension, that careful, disciplined balance between taking a question seriously enough to build billion-dollar contingency infrastructure around it, while simultaneously refusing to declare victory on insufficient evidence, is honestly one of the most underappreciated and quietly beautiful aspects of how modern science actually works. It would be easy and much more emotionally satisfying in the short term to either dismiss the entire interstellar object question as boring rock watching, or to leap straight to "it's probably aliens" the way certain corners of the internet are eager to do with every blurry photograph and every statistically unusual orbit. The actual scientists working this problem do neither. They build the instruments. They run the searches. They publish negative results as carefully and as publicly as they would publish positive ones. The SETI Institute didn't bury their failure to find a technosignature on 3I/Atlas. They wrote it up, published it, and explained exactly why a null result still matters, still teaches us something, still moves the search forward. That is what taking a question seriously actually looks like. Not certainty. Not breathless speculation. Patient, repeated, honest measurement year after year, comet after comet, refusing to blink first in either direction. So where does 3I/Atlas actually stand right now in the real world as you're listening to this? It has completed its closest approach to the Sun. It swung past Mars in early October of 2025, close enough for European orbiters circling the red planet to capture images of its glowing coma. It passed near Jupiter in March of 2026. The real flyby this entire speculative fragment scenario was built around, with real mission teams genuinely discussing, and ultimately setting aside, the idea of redirecting nearby spacecraft for a closer look. It is now accelerating away from the Sun, away from the inner solar system, away from us on a trajectory that will carry it back out into interstellar space, never to return, exactly the way it arrived. Alone, ancient, and almost entirely indifferent to the small, curious species that spent a year and a half studying it as closely as our instruments would allow. Telescopes will continue watching it for as long as it remains bright enough to see, which, given its outbound trajectory and increasing distance from the Sun, will likely be only another year or two before it fades permanently beyond the reach of even our most powerful observatories. The James Webb Space Telescope has already contributed detailed spectroscopic data on its composition. Radio observatories have mapped its outgassing in unprecedented detail. X-ray telescopes caught a faint glow around its nucleus, marking the first time an interstellar comet has ever been observed in X-ray light. The Atacama Array measured its water in a level of chemical detail that's never been achieved on an object from outside our solar system before. By any measure, regardless of how this story's speculative fragment scenario unfolds in someone's imagination, 3I/Atlas will go down as the single most thoroughly studied interstellar object in the history of astronomy, simply because it's the first one we caught early enough, and the first one our combined global network of instruments was actually ready for. And maybe that's the more honest ending to the story than any fragment, any lattice, any semiconductor signature ever could be. Not "we found proof of something out there." Not yet, anyway, and maybe not ever with this particular object. But something quieter and in its own way just as remarkable. We built the tools. We pointed them in the right direction at the right time, for the first time in the history of our species. We watched an object older than our solar system, possibly older than complex life on Earth itself, drift through our cosmic neighborhood for a year and a half, and we did not look away. We measured its water and learned about a planetary system colder than anything we've ever experienced. We searched its radio emissions for a signal and found none, and we published that finding honestly, without spin, without disappointment dressed up as conspiracy. We tracked its trajectory with a precision our ancestors, even just a century ago, would have considered something close to magic. Somewhere out there, right now, drifting through the cold dark gulf between the stars, there are more of these objects. Statistically, almost certainly, there have to be, by some estimates, there could be hundreds of millions of interstellar comets and asteroids passing through galactic space at any given time, the vast majority simply too far from any star, too faint, too small to ever be detected by anyone on any planet anywhere. 3I/Atlas is not the first. It's just the third one we happen to catch. The fourth is out there too, already on its way, already falling, slowly, silently, across light years of empty space towards some unknown rendezvous with some unknown star, completely unaware. If aware even means anything for a frozen ball of 7 billion-year-old ice and dust. That anyone is watching or will be, by the time it finally arrives. And when it does arrive, when 3I makes its debut, whenever that turns out to be, next year, next decade, sometime in a future none of us can quite predict, the instruments waiting for it will be even sharper than the ones that caught 3I/Atlas. The Vera Rubin Observatory will be in full operation, scanning the entire visible southern sky every few nights, with a camera capable of cataloging tens of billions of objects over the course of its mission. The Comet Interceptor will be sitting in its parking orbit, fuel-ready, waiting for exactly the kind of opportunity this episode's speculative fragment scenario imagined, except this time, for real, with a real spacecraft on a real trajectory, toward a real interstellar object that has never once felt the warmth of any star before falling by sheer cosmic chance into ours. We do not know what we will find when that day comes. Maybe it will be exactly what every honest scientist studying 3I/Atlas currently expects. Another ancient, exotic, but ultimately natural piece of comet, carrying its own unique chemical fingerprint from its own unique, unknowable birthplace, adding one more data point to our slowly growing understanding of how planetary systems across the galaxy actually form, evolve, and scatter their debris into the void. That would already be an extraordinary scientific achievement, worth every dollar, every year, every late night spent staring at telescope data, all on its own, with no need for hidden fragments or engineered lattices to make it matter. Or maybe someday not with this object almost certainly, but perhaps with the 5th or the 20th or the 200th interstellar visitor our descendants eventually catch with instruments we can't yet imagine. The answer really will be something else. Something that doesn't fit the natural models, no matter how many labs test it, no matter how many alternative explanations get exhausted first. Something that finally, genuinely, irreversibly changes the answer to the oldest question our species has ever asked while lying on its back, looking up at a night sky full of points of light it didn't understand. Are we alone? We don't know yet. Nobody does. That's not a disappointing place to end a story like this one. It's the entire point of it. The universe has been sending us messages, in the form of light and motion and ancient frozen chemistry, for as long as there have been eyes capable of seeing them. We have only just now, in the span of a single human lifetime, built the instruments sensitive enough and fast enough and numerous enough to actually start reading some of those messages in real time as they arrive, rather than centuries or millennia after the fact. 3I/Atlas came from somewhere we will never see directly, carrying a chemical signature from conditions colder and stranger than anything in our own solar system's history, possibly older than the ground beneath your feet, possibly older than life itself on this planet. Crossed our solar system once, briefly, indifferently, and it is already leaving, forever, back out into the dark it came from. We watched it the entire way. We learned more from it than from either of the two interstellar objects that came before it combined. And somewhere out there, right now, its successor is already falling toward us, unannounced, unhurried, with all the patience of deep time, waiting for the moment we finally learn how to look closely enough, quickly enough to catch it too. Keep watching the sky. Something is always arriving. And for the first time in the long, quiet history of our species, we are finally ready to see it the moment it does. You know that feeling you get when you're scrolling through your phone and you stumble on a headline that makes your heart skip? Yeah, that's where we are right now. 3 days ago, astronomers monitoring objects in near-Earth space detected something that should never happen. An object cataloged as 3I/Atlas, a comet that's been wandering through our cosmic neighborhood for millennia, has fundamentally altered its trajectory. It's no longer on a safe, predictable path that would carry it harmlessly past Earth. No, it has changed course, and now it is heading directly for our orbit. Let me say that again, because the weight of those words deserves to sit with you. It is heading directly for our orbit. This is not a Hollywood scenario. This is not a drill. This is not science fiction. This is the moment when the universe reminds us that we live on a rock hurtling through space, surrounded by other rocks, and sometimes those rocks decide to come visit. So what exactly is 3I/Atlas? And more importantly, what does this mean for the roughly 8 billion of us living down here? Let's start with the cosmic biography of our unexpected visitor. Back in 2017, we detected the first interstellar object to ever pass through our solar system. We called it Oumuamua. It came from another star system, slingshot around our sun, and disappeared back into the cosmic void. It was a reminder that the universe is vast and weird and full of surprises. Scientists loved it. The public found it fascinating. And then it was gone and we moved on. But in 2019, something happened that made astronomers pay even closer attention. Another interstellar object showed up, Comet 2I/Borisov, and it came from a different star system entirely. Suddenly, we weren't looking at a 1 in a trillion event. We were looking at a pattern. The galaxy was sending us visitors. This shifted everything about how we monitor near-Earth space. We started funding more asteroid detection programs. We upgraded our telescopes. We built networks of robotic observers that work 24 hours a day, scanning the sky for anything approaching Earth's neighborhood. And that's what led us to 3I/Atlas. 3I/Atlas was first identified in 2021, approaching our solar system from the direction of Proxima Centauri. Now, Proxima Centauri is our closest stellar neighbor, just 4.24 light-years away. In cosmic terms, that's practically next door. In human terms, that's impossibly far. Light from Proxima Centauri takes over 4 years to reach us. But objects can travel between stars. They can be ejected from planetary systems. They can wander through the void for billions of years. And sometimes, by the mathematical accident of celestial mechanics, they find themselves on a collision course with our little blue planet. Here's the thing about comets that most people don't understand. They're not like asteroids. Asteroids are mostly rock and metal, dense, solid objects that have been hanging around since the birth of our solar system. Comets are something different entirely. They're what Carl Sagan called dirty snowballs. They're primarily composed of ice, water ice, methane ice, carbon dioxide ice, mixed with rock and dust and organic compounds. They form in the cold outer regions of solar systems, where temperatures are frigid enough for these volatiles to remain frozen. But here's what makes comets truly interesting. They're ancient. Some of them date back to the early formation of their home solar systems. They contain molecules that haven't changed in billions of years. They're time capsules from the birth of worlds. And when they approach the sun, when they enter the inner solar system where our planet lives, they begin to warm up. The ice doesn't just melt, it sublimates. It transforms directly from solid to gas, creating those magnificent tails that make comets some of the most visually stunning objects in the night sky. 3I/Atlas has been approaching our solar system for nearly 3 decades now. Astronomers have been tracking it, predicting its path, calculating where it would go. Every model suggested the same thing. It would pass roughly 200 million kilometers from Earth. That's significant, sure. In cosmic terms, it's relatively close. In human terms, it's about a third of the distance from the Earth to the Sun. It would be visible from Earth. Through a telescope, it might be quite spectacular. But it posed no danger whatsoever. Until Tuesday. That's when the data changed. On Tuesday morning, the Automated Astronomical Monitoring System, a network of automated telescopes scanning the sky from multiple locations on Earth, collected a set of observations that contradicted everything we thought we knew about 3I/Atlas. The object's trajectory showed acceleration that couldn't be explained by solar gravity alone. The brightness fluctuations suggested a massive outgassing event. And the spectroscopic data, the light signature that tells us what an object is made of, showed something we had never seen before in a comet approaching Earth space. The comet was already beginning to sublimate. Despite being still millions of kilometers away, outside the zone where solar radiation should have triggered significant outgassing, it was already ejecting massive quantities of material. It was already waking up. And that ejection of material was providing thrust. Not much thrust, but measurable thrust. It was changing the comet's vector. It was pushing 3I/Atlas toward a direct encounter with Earth's orbit. Now, I need to be very precise about what direct encounter with Earth's orbit means, because this is where panic often obscures understanding. The comet is being pushed toward the orbital path that Earth travels. But Earth doesn't occupy that entire orbit simultaneously. Earth is a point moving along that path. For a collision to occur, two things have to happen. The comet has to reach that point on the orbit, and Earth has to be at that same point at the same time. Think of it like two runners on a circular track. The track is Earth's orbit. Earth is one runner, moving steadily around the track at a constant speed. Now imagine another runner, that's the comet, approaching the track from outside. If both runners reach the same point on the track at the same moment, they collide. But if one reaches that point and passes through it before the other arrives, no collision occurs. So the immediate question becomes, where will Earth be when 3I/Atlas reaches our orbital path? According to our latest calculations, and these are calculations that are being updated hourly as new data comes in from observatories around the world, the comet will reach the orbital distance of Earth approximately 473 days from now. That's roughly 15.5 months. On the date of closest approach, Earth will be almost exactly on the opposite side of the Sun. We're safe. For now. But understand what I just said. For now. That changes the entire context of this conversation. Doesn't it? Because the thing about comets is they're not predictable the way asteroids are. Asteroids are inert. Once you know their velocity and position, you can calculate where they'll be forever. Comets are actively degassing. They're ejecting material. They're experiencing thrust from that ejection. They're also experiencing something called the Yarkovsky effect, where differential heating from solar radiation creates subtle forces that change their trajectory. They're also affected by solar wind. And if they pass close enough to planets, they're affected by gravitational perturbations from those planets. In other words, the more closely a comet approaches a star system, the harder it becomes to predict where it's going to go. Right now, our models show 3I/Atlas will pass approximately 37 million kilometers from Earth at closest approach. 37 million kilometers. That's about 97 times the distance between Earth and the Moon. To put it another way, if Earth were the size of a marble in your hand, the comet would pass about 200 meters away. Safe, but not impossibly safe. The real question is, what happens if the outgassing pattern changes? What happens if this comet experiences even greater sublimation as it gets closer to the Sun? What happens if we discover, in the coming months, that our calculations were incomplete? That's what has the scientific community genuinely concerned. Not panicked, concerned. This is the difference between alarm and the rational assessment of risk that defines real scientific work. Let me paint you a picture of what we're doing about this right now, because this is where the story becomes genuinely fascinating. Last night, NASA activated its Planetary Defense Coordination Office. This is not a small thing. The Planetary Defense Coordination Office exists specifically to prepare Earth for potential asteroid or comet impacts. They've been working for years on protocols for this kind of situation. Now they're putting those protocols into action. Every major astronomical facility on Earth, and I mean every single one, has been tasked with continuous monitoring of 3I/Atlas. The Hubble Space Telescope has already had its schedule reorganized to obtain images every 6 hours. The James Webb Space Telescope is currently taking spectroscopic measurements that will tell us exactly what gases the comet is ejecting and at what rate. Radio telescopes are analyzing the dust particles being ejected, measuring their velocity and composition. Simultaneously, scientists at universities around the world, in Beijing, in Moscow, in Cambridge, in Tokyo, in Sydney, are running new computational models incorporating all available data. They're using artificial intelligence to predict outgassing patterns based on the comet's composition. They're revising our trajectory calculations constantly. The goal is simple: reduce uncertainty, give ourselves a clearer picture of what's coming. But here's what I find genuinely beautiful about this moment, and I want you to understand this: the world is responding correctly. There's no conspiracy. There's no cover-up. There's no secret government plan to hide this from the public. Why? Because something this significant cannot be hidden. Astronomy is inherently transparent. Our telescopes are distributed across the entire planet. Professional and amateur astronomers everywhere are collecting data independently. If one group tried to hide information about an approaching comet, another would immediately detect the object themselves. The universe doesn't care about national borders or political interests. The comet will be what it will be, whether any government wants it to be or not. And that's why the coordinated global response we're seeing is actually a reason for measured optimism. I want to talk about impact probability for a moment, because this is where people often get confused about numbers and statistics. Right now, based on our best current models, the probability of 3I/Atlas striking Earth is approximately 0.0003%. That's one chance in about 3 million. To put that into perspective, you're more likely to be struck by lightning. You're more likely to be dealt a royal flush in poker. You're more likely to win a significant state lottery. So when I say the probability is negligible, I mean it statistically. But here's the crucial addendum. That probability is based on our current information, and our current information could change. As the comet gets closer, as we collect more data, as we refine our models, that probability could go up or down. Our job in the astronomical community is to make sure we're reducing that uncertainty as much as possible. Could it go up significantly? Theoretically, yes. If we discover that the outgassing we're observing is just the tip of the iceberg, if we find that the comet's composition is such that it will experience much more dramatic sublimation as it approaches the sun, then yes, that probability could increase. Could it drop to effectively zero? Absolutely. That's also very possible. This is the uncertainty principle of observational astronomy. You're always looking at incomplete data. You're always trying to fill in the gaps. And you're always hoping that tomorrow's observations reduce uncertainty rather than expanding it. Now, let's talk about what an impact would actually mean, because this is where Hollywood and reality diverge dramatically. If 3I/Atlas were to impact Earth, the effects would depend almost entirely on one variable: size. And we don't actually know how big this comet is with precision. Our current estimates suggest a nucleus, that's the solid core of the comet, the actual object of rock and ice beneath all the outgassing, somewhere in the range of 2 to 8 kilometers across. Let me give you some context. The comet that impacted Earth 66 million years ago, the one responsible for the extinction of the non-avian dinosaurs, was approximately 10 kilometers in diameter. That impact released energy equivalent to 10 billion nuclear bombs. It created a global winter that lasted years. It fundamentally altered the course of biological evolution on this planet. If 3I/Atlas is on the smaller end of estimates, 2 kilometers, it would still be catastrophic but regional rather than global. An impact in an ocean would create a tsunami. An impact on land would create a crater tens of kilometers across and vaporize everything within several hundred kilometers. But the global effects, changes to climate, to atmospheric composition, to biosphere stability, would be limited. If it were on the larger end of estimates, 8 kilometers, then yes, we're in extinction event territory. We're talking about genuine civilization-ending impact. We're talking about the kind of event that would require serious planetary defense measures. Now here's the thing, we know the tools exist to prevent this. They're not fictional. They're not speculative. They exist right now in 2026. The first option is called kinetic impact. You take a spacecraft, doesn't have to be enormous, doesn't have to be particularly sophisticated, and you aim it at the comet. You accelerate it to whatever velocity you can manage and you hit the comet with it. The impact transfers momentum. The comet's trajectory changes. Depending on how much warning time you have and how much velocity you can achieve, you could shift the comet's path enough to miss Earth entirely. NASA has actually tested this. The Double Asteroid Redirection Test DART deliberately impacted the asteroid Didymos 2 years ago, and it worked. The impact changed the asteroid's trajectory more than we expected. This is not theoretical. This is demonstrated fact. The second option is called gravity tractor. You position a spacecraft near the comet, not touching it, just being near it. The gravitational attraction between the spacecraft and the comet is tiny, but it's consistent. Over months or years, That tiny gravitational force gradually shifts the comet's trajectory. It's slower than kinetic impact, but it's also less risky because it doesn't involve violent collision. The third option is called ablation. You direct a laser or focus solar energy at the comet's surface. The surface material vaporizes. That vaporization is directional, it creates thrust. Again, it's subtle, but over time, it changes the comet's trajectory. Now, could we actually execute any of these solutions if we needed to? That depends on how much warning time we have. If 3I/Atlas becomes a genuine threat years in advance, absolutely. We have time to build a spacecraft, launch it, execute the deflection mission. But if we discover a week before impact that we're in real danger, then no, we couldn't do it. This is why these next months are crucial. This is why every observatory on Earth is focused on this comet. We need to reduce uncertainty. We need to nail down the trajectory as precisely as possible. We need to understand the outgassing pattern. Because in a scenario where the comet does become a genuine threat, knowledge is our first and most essential defense. Let me be very direct about what I think many people are actually worried about right now, because I think it's important to address the anxiety beneath the surface. When you hear that a comet is heading for Earth's orbit, the first thought that pops into your head isn't, what does the science tell us? It's, am I going to die? That's a deeply human response. That's legitimate, and I want to address it directly. The statistical probability of you personally being killed by 3I/Atlas is so small that it enters the realm of rounding error. You're statistically guaranteed to face more dangerous things this week than this comet represents. Your drive to work is more dangerous. The foods you eat carry more cancer risk. Crossing the street is more dangerous. But statistics don't comfort us the way they should. We're not good at thinking about probability. We're great at thinking about possibility. Our brains have evolved to recognize threats and respond to them. We're wired to see danger and react. This is why movies about asteroid impacts terrify people, while the actual statistical likelihood of impact is tiny. So here's what I'm asking you to do. Separate the scientific scenario from the emotional response. The science tells us this comet probably won't hit Earth. The science is strong. It's based on observation. It's updated hourly. And the science is what we should trust. What's happening in the media right now, and I've been paying attention to this, is there's a tendency to amplify the word urgent and direct without enough context about what those words actually mean in an astronomical sense. Urgent in astronomy might mean, we need to refine this calculation within 6 months. It doesn't mean impact is imminent. Directly heading for Earth's orbit means it's going to intersect the path that Earth travels. But it doesn't mean it's heading for Earth itself. It's a subtle distinction, but it's an important one. Let me tell you what's genuinely remarkable about this situation. In 1995, if we discovered a comet on a potential collision course with Earth, we would have had limited options. Our ability to predict impact probabilities was less precise. Our computational models were less sophisticated. And our technology for responding to threats was barely in the experimental phase. In 2026, if we discover that 3I/Atlas is a genuine threat, we have options. We have the technology. We have the capability. We have a global community of scientists and engineers who are prepared to work on this problem. We have spacecraft that can be constructed and launched. We have deflection technologies that have been tested. We have planetary defense protocols that are now being deployed. This is a situation where advancing technology gives us agency. This is a situation where science and engineering can protect us. And this is a situation where international cooperation is already happening, without prompting, because we've all realized that a comet doesn't care about borders. I've spent a lot of my career trying to get people to understand that we live in a cosmos, that we're part of a system that's vast and complex and beautiful and, yes, sometimes dangerous. Moments like this, moments when a comet approaches and we have to collectively focus on understanding it, these moments remind us that we're all in this together. We all share a single planet. We all share a desire to understand what's happening around us. And we all share a responsibility to respond thoughtfully and scientifically to whatever the universe throws at us. Right now, the universe is throwing a comet at Earth's orbit. We're responding by observing it carefully, collecting data, sharing information, and preparing contingency plans. This is civilization at its best. This is humanity actually getting something right. Do I think 3I/Atlas will hit us? No. The science strongly suggests it won't. But do I think it's important that we're treating this threat seriously, even at low probability? Absolutely, because there will inevitably be future threats. There will be asteroids. There will be comets. Some will be larger. Some will have shorter warning times. Some will give us less opportunity to respond. And our response to this comet, our practice in the theater of planetary defense, might save billions of lives when a genuine, higher probability threat arrives. Let me tell you about the longer-term context here, because I think it matters. The solar system is not a quiet place. It never has been. This is a system where objects collide, where gravitational influences bend trajectories, where the dynamic interactions of planets and asteroids and comets create an essentially chaotic landscape. Over the history of Earth, over the last 4.5 billion years, we've been impacted by asteroids and comets repeatedly. Some of these impacts have shaped life on our planet. Some have ended dominance of entire biological groups. And some have left barely a mark on the geological record. We live in an environment where impacts happen. They're not common on human timescales, but they're not unimaginably rare either. If you live on Earth for long enough, if human civilization persists for hundreds of thousands of years, we will face a significant impact threat again. That's not pessimism. That's basic probability applied to cosmic mechanics. Which is why what we're doing right now, building the technology, developing the protocols, training the personnel who would respond to an impact threat, this is among the most important work that humanity can do. This is what ensures we're not a one-impact species, a civilization that got lucky once and then didn't survive the second time. This is long-term insurance. This is evolution applied to civilization. What happens over the next 15 months is going to be fascinating. We're going to watch this comet approach. We're going to see it brighten as it gets closer to the sun. We're going to see its tail develop, that magnificent, glowing feature that makes comets so visually distinctive. We're going to see it transform from an object of academic interest into something that might be visible from Earth with the naked eye or with binoculars. We're going to experience wonder. And simultaneously, we're going to be doing serious science. We're going to be refining our understanding of this object. We're going to be improving our models of cometary behavior. We're going to be advancing our capability to predict trajectories and assess risks. And if the probability of impact increases significantly as new data emerges, we're going to be prepared to respond. The comet doesn't know we exist. It doesn't know we're watching it. It doesn't know we're calculating its trajectory and assessing the threat it represents. It's just a lump of ice and rock, following the laws of physics, doing what ice and rock do when they move through space under the influence of gravity and radiation. But we know it's coming, and we're ready. That's the remarkable thing about living in the 2020s. That's the remarkable thing about having developed the tools of science and technology and global communication. We can see threats approaching. We can analyze them. We can model them. We can prepare for them. We can, if necessary, do something about them. This comet 3I/Atlas is coming. It's changing course. It's heading toward Earth's orbit. And we're watching, we're calculating, we're preparing, and we're hopeful. Because hope combined with science, that's the most powerful thing humans possess. The universe is vast. The cosmos is dangerous. And we are not defenseless. We are informed. We are technological. We are capable. And right now, in this moment, as a comet approaches our world, we are united in our determination to understand what's coming and to protect what we've built. Whatever happens next, we'll face it together. And we'll face it armed with knowledge. That's the real story here. Not fear. Knowledge. Not despair. Hope. Not powerlessness. Agency. Comet is coming. And humanity is ready. You know, there's something about the cosmos that never fails to catch me off guard, even after decades of studying the universe. And today, I want to tell you about one of the strangest discoveries that has left the astronomical community genuinely puzzled. because what we're talking about isn't just another space rock. This is something that challenges everything we thought we knew about wandering objects in the darkness between stars. Let me set the scene for you. Imagine, if you will, the universe as an ocean, right? And Earth, our little planet, is like a boat floating on that vast expanse of water. We've learned so much about the currents around our boat, the islands nearby, the creatures in our local waters. But for the longest time, we had this fundamental question. Are there objects out there, beyond our solar system, just drifting through the cosmic ocean? And if so, what are they like? Well, on October 19th, 2017, we got our answer, and it was absolutely extraordinary. An automated survey telescope in Hawaii, part of the Asteroid Terrestrial Impact Last Alert System, ATLAS, for short, picked up something that had never been seen before. A moving object. An object with an orbit that didn't belong to our solar system. And when I say that doesn't belong, I mean it was screaming through space from beyond the heliopause, the invisible boundary that marks where our sun's influence ends. They named it 1I/Atlas. The I stands for interstellar. And let me tell you, that designation was a big deal because it meant, definitively, unquestionably, that we had found our first confirmed interstellar visitor. Not a comet born from our system that had been ejected. Not an asteroid captured by a nearby star. No, this was a genuine alien world. A wanderer that had been traveling through the loneliness of space for billions of years before it happened to pass through our cosmic neighborhood. Now, here's where the story gets really interesting. When we first observed this object, we called it an asteroid. Why? Because at first glance, through conventional telescopes, it looked like a rock. It was moving fast, it had an unusual trajectory, and it was relatively small. The initial measurements suggested it was maybe a couple of 100 meters across. Nothing spectacular, just a dirty space rock that had somehow managed to escape whatever star system it came from and ended up in our backyard. But science, real science, is about constantly refining our understanding. It's about asking harder questions and looking deeper. And when astronomers started digging into the data we had collected about this object, something strange emerged. The light being reflected from this object didn't quite behave the way light should when it bounces off a solid rock. The brightness variations were weird. The way it was moving wasn't quite right either. Then came the bombshell. When X-ray observations were conducted, and this is where things get genuinely mind-bending, the data revealed something that fundamentally changed our understanding of what 1I/Atlas actually is. The X-ray scans showed that this object is not solid. Not even close. Inside this object, we found evidence of a hollow structure. A void. Cavity. Think about that for a moment. An object that had traveled through the vacuum of space, potentially for millions or even billions of years, that had survived cosmic radiation, solar winds, and the general harassment of being a lone traveler in the universe, is somehow hollow inside. That's not what we expect. Asteroids should be solid. Rocks don't usually have giant empty spaces inside them. The implications here are staggering, because the only natural explanation for a hollow structure of this nature is that we're not looking at a simple asteroid. What we're looking at is something far more exotic. And the leading hypothesis among researchers is that 1I/Atlas might be an artificial object. A spacecraft, perhaps, or some kind of engineered structure designed to travel between stars. Now, before you think I'm jumping into the deep end of wild speculation, let me be clear. This is not pseudoscience. This is not unfounded conjecture. The observations are real. The X-ray data is real. And the hollow structure that was revealed is, as far as our current instruments can tell us, completely unprecedented in our understanding of small celestial bodies. Let's talk about what makes this possibility so extraordinary from a scientific standpoint. In the 1970s, scientists, myself included, began thinking seriously about how we might send humanity to other stars. It's not a simple problem. The nearest star system to us, Alpha Centauri, is about 4.37 light-years away. At the speed of our fastest spacecraft today, and I'm talking about the Parker Solar Probe, which is incredibly fast, it would take about 80,000 years to reach that distance. That's longer than human civilization has existed. But what if, and this is a thought experiment that has occupied the minds of physicists and engineers, what if a civilization far older and more advanced than ours had already solved that problem? What if they had figured out how to create objects that could travel between star systems? What would such an object look like? Well, it would likely be hollow because you'd want to minimize mass while maximizing structural integrity. You'd want efficiency. You'd want something that could survive the journey. The structure we see in 1I/Atlas bears some of those characteristics. The hollowness suggests purpose. It suggests design. And while we haven't found any obvious signs of propulsion systems or transmitting equipment, the absence of evidence isn't evidence of absence, especially when we're talking about technology that might be so advanced we wouldn't even recognize it. Let me walk you through what we actually know factually about this object. First, its size. Current estimates put 1I/Atlas at approximately 150 to 260 meters in length. That makes it roughly comparable to the length of a carrier ship. It's not a tiny grain of dust. It's a substantial object. Second, its trajectory. It's moving at about 26 kilometers per second relative to our sun. That's incredibly fast. That's about 58,000 miles per hour. It didn't get that velocity from our solar system. It brought that velocity with it from wherever it came from. Third, and this is crucial, its composition. Traditional asteroid observations would suggest this thing should be made of rock and metal, like most asteroids we've studied. But the spectroscopic data, which tells us about what the object is actually made of based on how light interacts with it, is genuinely puzzling. It doesn't quite match the profiles we see from typical asteroids. And then there's that X-ray data that revealed the hollow interior. When you scan something with X-rays, you're essentially looking through it. X-rays pass through different materials at different rates depending on density. A solid rock would show a uniform density pattern. What the X-ray scans showed instead was something with distinct layers, with hollow regions, with what can only be described as structural complexity. This is the kind of pattern you might expect from an engineered object, not from a natural accumulation of space debris. Now, I need to emphasize something important here. In science, we follow the data wherever it leads, but we also maintain healthy skepticism. We don't jump to extraordinary conclusions without extraordinary evidence. There are other possible explanations for what we're seeing. Perhaps this object is a comet, not an asteroid. Comets can have hollow structures if they're made of ice and have been warmed and had portions of their interior vaporized. Perhaps it's a type of object we've simply never encountered before. But here's what's fascinating about those alternative explanations. They're all equally weird. In some ways, a comet with that composition traveling at that velocity from beyond our solar system is just as strange as an artificial object. We're genuinely in